There is a moment every single night where the sky above you becomes something almost impossible to comprehend. The darkness that settles in between the stars is not emptiness. It is not nothing. It is a canvas stretched across distances so enormous that no human mind has ever truly processed them without some part of the brain quietly shutting down in protest. We live on a rock, a spinning, hurtling, unremarkable little rock that orbits a fairly average star somewhere near the edge of one of roughly 2 trillion galaxies. And yet for most of human history, we thought we were the center of it all. We thought the stars revolved around us. We thought the universe was small and knowable and built specifically for our benefit. And then, slowly, science tore that idea apart, piece by piece, discovery by discovery, until all we had left was the raw, unfiltered truth that the universe is so large, so old, and so strange that the most accurate thing you can say about it is that we barely understand any of it at all. That is what we are going to explore today. Not in a sanitized, textbook kind of way, but deep, real, layered. We are going to move through space the way space actually is. Enormous, terrifying, breathtaking, and relentlessly weird. We are going to talk about black holes that defy physics, planets that rain glass sideways at 2,000 miles per hour, stars so massive that if you put them where our sun is, they would swallow everything out past Jupiter, galaxies that are locked in slow-motion collisions that will reshape the cosmos a billion years from now, and moments in the history of human spaceflight that will make you question what it really means to be brave. We are going to go everywhere, and we are going to take our time. Let us start where perhaps the most dramatic story in space science begins, with the death of stars, because what happens when a star dies is one of the most violent and consequential chains of events in the known universe. When a star like our sun exhausts its hydrogen fuel, and it will, about 5 billion years from now, it does not simply go dark, it expands. It swells outward in a last desperate gasp, growing into a red giant that will engulf Mercury, then Venus, then almost certainly Earth. For a brief period, the bloated outer shell drifts away from the core and becomes a glowing planetary nebula, a shell of ionized gas lit from within by what remains of the star's hot, exposed core. That core, no longer able to sustain fusion, collapses under gravity into something called a white dwarf. A white dwarf is roughly the size of Earth, but it contains the mass of a star. A teaspoon of white dwarf material would weigh somewhere around 5 tons on Earth. It is dense beyond intuition. It glows white-hot from the heat of its collapse and will continue to radiate that heat for hundreds of billions of years, slowly cooling, assuming, of course, that nothing disturbs it. But not every star ends that gently. Stars that are significantly more massive than our Sun, 8 times the mass or more, meet a very different fate. They do not drift away as planetary nebulae. They explode. They become supernovae, and the scale of a supernova is so far beyond human intuition that it takes several passes to even begin to appreciate it. In a matter of seconds, a supernova releases more energy than our sun will emit across its entire 10 billion year lifespan, not per day, not per year, its entire lifespan, in seconds. The shock wave from a supernova can travel tens of light years outward, compressing and heating the interstellar gas it passes through, sometimes triggering the formation of entirely new stars in its wake. The dying star, in its final moments, seeds the next generation of stars with heavy elements, iron, nickel, gold, uranium, that could never have been made any other way. Every atom of gold in every piece of jewelry on Earth was forged in the explosion of a star that died before our solar system existed. What is left behind after a supernova depends on the original mass of the star. For stars between roughly 8 and about 20 times the mass of our sun, what remains is one of the most extreme objects in the universe, a neutron star. A neutron star forms when the collapsing core of the exploding star is compressed so violently that electrons and protons are forced together, producing neutrons, and the entire mass of the core, which might be 1.5 to 2 times the mass of our sun, is packed into a sphere roughly 12 to 15 miles across, the width of a small city. With the mass of a star, the density inside a neutron star is so extreme that if you dropped a marshmallow onto the surface of one, it would hit with the energy of a nuclear bomb. Not because of any exotic physics, just because of gravity. The surface gravity on a neutron star is approximately 200 billion times stronger than the surface gravity of Earth. Standing on one, which is not possible for obvious reasons, You would be crushed to a layer thinner than an atom in less than a millisecond. The magnetic fields around neutron stars are equally incomprehensible. A typical neutron star has a magnetic field roughly 1 trillion times stronger than Earth's. That is not a typo. 1 trillion times stronger. These magnetic fields funnel radiation from the poles of the neutron star into tight beams, and if the star is rotating in the right orientation, those beams sweep past Earth like the rotating beam of a lighthouse. We call these objects pulsars, and they are so regular in their timing. Some pulsars complete their rotation hundreds of times per second with a precision that rivals atomic clocks, that when Jocelyn Bell Burnell first detected the signals in 1967, the team briefly, seriously, considered whether they might be signals from an alien civilization. They labeled the source LGM-1, which stood for Little Green Men. It was not aliens, it was physics. But the fact that the laws of physics can produce something so mechanical and precise without any intelligence behind it is in its own way even more unsettling. Some neutron stars spin so fast they are called millisecond pulsars. The fastest one ever recorded, PSR J1748-2446 AD, completes 716 rotations per second. The equatorial surface of that star is moving at roughly a quarter of the speed of light. These stars are spinning so fast that if they were any more massive, the centrifugal force would theoretically begin to break them apart. They exist right at the edge of what matter can survive. And then there is the object at the extreme end, the thing a neutron star becomes if it is too massive even to hold itself together as compressed neutrons. A black hole. And black holes are where the story of space physics becomes something that stops resembling anything from ordinary experience and enters a place where your intuitions about time, space, and reality simply cannot follow. A black hole forms when the collapsing core of a massive star has so much mass concentrated in so little space that gravity overwhelms every known force in the universe. The matter collapses to a point of infinite density, a singularity, surrounded by a boundary called the event horizon. The event horizon is not a physical surface, it is just a threshold, the point of no return beyond which escape velocity exceeds the speed of light. Once you cross it, you are not being held in place by something solid. You are simply in a region of space where all paths in spacetime, including paths moving at the speed of light, lead inward, not toward the singularity because it pulls you. Toward the singularity because that is the only direction that exists inside a black hole. The geometry of spacetime itself points inward. This is one of the genuinely terrifying things about black holes that often gets lost in casual conversation. Crossing the event horizon does not feel like hitting a wall. If you fell into a large enough black hole, you might cross the event horizon without sensing anything unusual at all. You would still see the universe around you, though increasingly distorted. You would still feel like you were floating in space. But you would have no way of knowing that every possible future for you now leads, inescapably, to the singularity. Escape would be as impossible as traveling into the past. Not difficult, impossible. Like asking a river to flow uphill, the laws of physics would have simply rearranged themselves around you. What you would notice, before crossing, is the visual distortion caused by the black hole's gravity-bending light. Light from stars behind you would arc around the black hole and appear in front of you. The sky would seem to fold in on itself. Directly ahead, where the black hole sits, there would be a sphere of absolute darkness surrounded by a blazing halo of distorted starlight. The photon sphere, where photons orbit in tight circles, creating a glowing ring around the dark center. The image of a black hole we captured in 2019, M87 STRA, the first ever photographed, showed exactly that. The orange asymmetric ring of superheated gas surrounding the dark shadow of the event horizon. That image represented a decades-long international collaboration, an Earth-sized virtual telescope built from synchronized radio observatories spanning the entire planet, and a dataset so large it had to be physically flown on hard drives to the processing centers because it was too large to send over the internet. M87-2 is not a small black hole. It is 3 billion times the mass of our Sun, and it sits in the center of the galaxy Messier 87, which is itself 65 million light-years away. Everything we know about it came from light that left it 65 million years ago, light that began its journey toward Earth when non-avian dinosaurs had only recently gone extinct. It traveled across intergalactic space for 65 million years and was then captured by our radio telescopes and turned into a photograph. At the center of our own galaxy, the Milky Way, sits a black hole called Sagittarius A, pronounced Sagittarius A star. It is about 4 million times the mass of our Sun. It is roughly 26,000 light-years from Earth. On a clear night far from city lights, you are not exactly looking at it. It sits behind dense clouds of dust and gas in the direction of the constellation Sagittarius, but it is there, at the center of everything you live inside. Sagittarius A itself is relatively quiet right now, as supermassive black holes go. It is not currently eating enough material to produce the kind of active galactic nucleus that makes some other galaxies blaze with quasar light. But periodically something falls too close, a cloud of gas, sometimes a star, and it flares briefly. In 2019, astronomers observed it brightening by a factor of 75 times normal in just a couple of hours. No one is entirely sure what triggered it. Sagittarius A is surrounded by a cluster of stars called the S cluster, which orbits so close to the black hole that their speeds become extraordinary. One star, designated S2, travels at roughly 3% the speed of light at its closest approach to Sagittarius A SA. When S2 passes close enough, general relativistic effects are measurable. Time actually passes slightly slower for S2 at its closest point than it does at its farthest. Astronomers have tracked S2 through multiple complete orbits, and its behavior matches the predictions of general relativity with extraordinary precision. Einstein's equations, written in 1915 without any data from black holes, which weren't even called black holes until the 1960s, predicted exactly what we observe. Supermassive black holes like Sagittarius A star are found at the center of nearly every large galaxy. What made them so large is still not entirely resolved. The leading theories involve either the slow accumulation of mass over billions of years of feeding, the merger of smaller black holes, or possibly the rapid collapse of enormous gas clouds in the early universe into direct collapse black holes of perhaps 100,000 solar masses that then grew from there. The largest supermassive black holes we have discovered are staggering even by these standards. The black hole at the center of a galaxy called TUN 618, a quasar in the constellation Canes Venatici, has a mass of about 66 billion times our Sun. Its event horizon is larger than our entire solar system. If you replaced Sagittarius A star at the center of the Milky Way with 2N618, its event horizon would extend past the orbit of Pluto. And yet, as massive as these objects are, the event horizons of black holes, at least stellar mass black holes, are startlingly small. A black hole with the mass of our Sun would have an event horizon with a radius of roughly 3 kilometers. The Schwarzschild radius of any object is just its mass in kilograms multiplied by twice the gravitational constant, divided by the speed of light squared. If you compressed Earth into a black hole, which would require somehow compressing all of Earth's mass into a sphere about the size of a marble, its event horizon would have a radius of about 9 millimeters. The Earth would still have all of its mass. The Moon would still orbit it. The only thing that would change is that light could no longer escape from the 9-millimeter sphere at the center. But here is the thing. Hawking radiation suggests that black holes are not permanent. In 1974, Stephen Hawking published what is now considered one of the most profound results in theoretical physics, that black holes slowly evaporate over time. The mechanism involves quantum fluctuations near the event horizon, where pairs of virtual particles are constantly being created and annihilated. Near the horizon, one particle falls in and one escapes, and the black hole loses a tiny amount of mass. For stellar mass black holes, this evaporation is so slow as to be utterly negligible, far slower than they can accumulate mass from the cosmic microwave background radiation alone. But given enough time, in a universe that has grown cold and dark enough, black holes will evaporate. A black hole with the mass of our Sun would take roughly 2 × 10 to the 67th power years to evaporate completely. That is not a duration any human notation system is really built to convey. The current age of the universe is about 13.8 billion years, a number with 10 digits. The evaporation timescale of a black hole is a number with 68 digits, and the evaporation produces something called the black hole information paradox. When a black hole forms, it swallows information, the quantum states of every particle that has ever fallen into it. But Hawking radiation is thermal radiation. It is random. It appears to carry no information about what went in. If black holes truly destroy information, that violates one of the deepest principles of quantum mechanics, which says information is conserved, it cannot be destroyed. The universe keeps a ledger, and for decades the question of what happens to the information inside a black hole was considered one of the most important unsolved problems in physics. Recent work, especially involving a theoretical tool called the island formula and a concept called the page curve, suggests that information is indeed encoded in the Hawking radiation, but doing so requires some of the deepest and strangest ideas in theoretical physics, involving the way the interior of the black hole is connected to its exterior through microscopic quantum channels. It is not resolved. Physicists are still working on it. Let us now move away from the extreme compactness of black holes and toward another kind of extreme, the extreme scale of galaxy clusters, because the largest structures in the universe are things that make individual galaxies look like individual grains of sand, and understanding them changes how you see the universe as a whole. Galaxies do not exist alone. They exist in groups and clusters and superclusters, bound together by gravity, and those superclusters are themselves arranged in enormous filamentary structures called the cosmic web, long threads of matter separated by vast empty regions called cosmic voids. The cosmic web is the large-scale structure of the universe, and it looks in simulations and in observations almost exactly like a neural network, like a brain. Long filaments of galaxies connected at nodes with enormous dark voids between them. It is visually, aesthetically striking in a way that has led many people to suggest, not entirely seriously, but not entirely unseriously either, that perhaps the universe itself is something like a mind. The universe is not a mind, but the resemblance between the cosmic web and biological neural networks emerges from the same mathematical principles that govern the growth and clustering of branching, connected structures. So it is a legitimate observation even if it points to physics rather than consciousness. The largest known structures in the observable universe include things like the Hercules Corona Borealis Great Wall, a galactic filament that spans roughly 10 billion light-years. The observable universe is only about 93 billion light-years in diameter. This one structure is 10 billion light-years long. It is so large that it arguably challenges the cosmological principle, the assumption that the universe is homogeneous and isotropic on large enough scales. If structures this large exist, how large do they get? We do not know. The Laniakea supercluster, which is the supercluster our own Milky Way belongs to, is about 500 million light-years across and contains roughly 100,000 galaxies, including our own. It was only mapped in detail in 2014, when astronomers used measurements of galaxy velocities to map the gravitational landscape of our region of the universe. Laniakea means immeasurable heaven in Hawaiian, a name chosen to honor the Polynesian navigators who used the stars to cross the Pacific. Inside Laniakea, there is an enormous region of gravitational attraction called the Great Attractor, a concentration of mass in the direction of the constellation Centaurus, toward which the entire Laniakea supercluster, including us, is flowing. The Milky Way is moving toward the Great Attractor at roughly 600 kilometers per second. It is not a single object. It is a complex of galaxy clusters, dominated by a structure called the Norma cluster, that together exert a gravitational pull on everything around them. We are being drawn toward it. We will never arrive. The accelerating expansion of the universe will eventually pull everything apart far before the journey is complete. The expansion of the universe, driven by what we call dark energy, is one of the most mysterious forces in physics. We discovered the accelerating expansion in 1998 when two independent teams of astronomers, studying distant Type 1a supernovae as standard candles for measuring cosmic distances, found that the supernovae were farther away than expected. The universe was not just expanding, it was expanding faster over time. This was so surprising that the two team leaders, Saul Perlmutter and the pair of Brian Schmidt and Adam Rees, shared the Nobel Prize in Physics in 2011 for the discovery. What is driving the acceleration? We call it dark energy, but that name is more a placeholder than an explanation. It is the energy of empty space itself, a property of the vacuum that causes space-time to expand. It constitutes about 68% of the total energy content of the universe. We do not know what it is. We cannot detect it directly. We infer its existence from the behavior of the universe at the largest scales. This is the great humbling truth of modern cosmology. The two dominant components of the universe are mysteries. Dark energy, which we cannot directly detect, makes up 68%. Dark matter, which we also cannot directly detect, makes up about 27%. The ordinary matter that makes up everything we have ever seen, touched, measured, or built, every star, planet, gas cloud, human being, and piece of technology, constitutes only about 5% of the universe. We live in the thin, visible fraction of a cosmos we do not understand. Dark matter is inferred from its gravitational effects. Galaxies rotate in ways that make no sense if the only mass present is the mass we can see. The outer edges of spiral galaxies rotate at roughly the same speed as the inner regions, rather than slowing down as Newton's laws predict for a mass concentrated near the center. Something else is there, holding the galaxy together, contributing mass without emitting or absorbing light. Galaxy clusters bend light from objects behind them far more than they should given their visible mass, a phenomenon called gravitational lensing. Dark matter halos extend well beyond the visible boundaries of galaxies and clusters. We can map the distribution of dark matter through careful measurements of this gravitational lensing. We know where it is. We just do not know what it is. Candidates include weakly interacting massive particles, WIMPs, which are hypothetical particles that interact only through gravity and the weak nuclear force, passing through ordinary matter almost without effect. Billions of dark matter particles may be passing through your body every second if WIMPs are real. We have not yet detected them directly. Or possibly dark matter is something stranger, primordial black holes formed in the early universe, or axions, or sterile neutrinos. The experiments to detect dark matter directly are running. The results so far are silence. But science often works this way. The answer is out there, and we have simply not yet found the right key to unlock it. Now let us talk about the planets in our own solar system, because they are strange in ways that often do not get the credit they deserve. People talk about going to Mars or exploring Europa, but the actual physical facts about these worlds, even the ones we have known about for centuries, are genuinely unsettling once you examine them carefully. Let us start with Mercury, the closest planet to the Sun, which immediately defies what most people expect. You might think Mercury, being closest to the Sun, would be the hottest planet. It is not. Venus is hotter. Mercury has almost no atmosphere, a thin exosphere of sodium, oxygen, hydrogen, and other trace elements that provides essentially no insulating blanket. The side facing the Sun bakes at temperatures up to 430 degrees Celsius. The side facing away from the Sun, during Mercury's long night, drops to -180 degrees. That is a temperature range of over 600 degrees between day and night on the same planet. Mercury's day is extraordinarily long. It takes 59 Earth days to complete one rotation, but only 88 Earth days to complete one orbit around the Sun, which means one Mercurian day is actually longer than a Mercurian year in one sense, and the relationship between its rotation and orbit produces a bizarre phenomenon where, if you stood on Mercury's surface, the Sun would rise, stop, briefly move backward across the sky, then continue forward, appearing twice in a single solar day from some locations. Mercury is also shrinking. As its iron core cools, it contracts, and the surface buckles in great cliffs called lobate scarps. One of them, Carnegie Roops, is 3 kilometers high and over 500 kilometers long. The planet is actively contracting, leaving these geological wrinkles across its face. Venus, the second planet, is in many ways the most harrowing world in the solar system, at least among the rocky planets. It is almost exactly Earth's size. It has similar mass. It formed at the same time, and it is utterly, comprehensively hostile to life as we know it. The surface pressure is about 92 times Earth's atmospheric pressure, the equivalent of being nearly a kilometer underwater. The average surface temperature is around 465 degrees Celsius, not because Venus is closer to the Sun than Earth, but because of a runaway greenhouse effect fueled by its thick carbon dioxide atmosphere. That temperature is consistent across the entire surface, including the poles and through the entire night side. There is no cold spot on Venus. The heat penetrates everywhere, stored by the dense atmosphere that blankets the entire planet evenly, and it rains sulfuric acid on Venus, not at the surface where it is too hot, but higher up in the cloud layers where temperatures are cooler. The rain evaporates before reaching the surface, cycling through the cloud layers. The clouds of Venus are thick enough that, from space, the planet appears as a nearly featureless white sphere. You cannot see the surface with visible light. We only know what Venus's surface looks like because of radar mapping missions, primarily the Soviet Venera landers, which survived the surface conditions for up to 2 hours before the extreme heat and pressure destroyed them, and the Magellan spacecraft, which radar mapped the entire globe from orbit in the early 1990s. And here is one of the most disquieting facts about Venus. It rotates backward. If you were watching Venus from above the solar system's north pole, it spins clockwise, opposite to Earth, opposite to most planets, and it spins extremely slowly. A Venusian day is 243 Earth days. But a Venusian year is only 225 Earth days. So on Venus, a day is longer than a year, and the sun for a Venusian would rise in the west and set in the east. Why Venus rotates this way is still debated. The leading theories involve either a giant impact that flipped its rotation billions of years ago, or a complex gravitational interaction between the planet's dense atmosphere and solar tides over very long timescales. Either way, it is wrong. It is backward. Venus is a mirror of Earth that went catastrophically wrong. Mars, the fourth planet, is familiar from thousands of science fiction stories and an increasing number of real robotic visitors. But the real Mars has some features that still manage to surprise. Olympus Mons, the largest volcano in the solar system, is 21 kilometers high, nearly 2.5 times the height of Everest, and so wide at its base, about 600 kilometers across, that if you stood at the summit, the edges of the volcano would be below the horizon. You would not be able to see that you were on a volcano. You would just be standing on a high, gently sloping plain, looking out at a red landscape disappearing into the curvature of the planet. Similarly, Valles Marineris, the Great Canyon system of Mars, stretches over 4,000 kilometers, is as much as 7 kilometers deep, and is roughly 10 times longer and 5 times deeper than the Grand Canyon. If it were on Earth, it would span the continental United States from coast to coast. It dwarfs every comparable geological feature on our planet. Mars once had liquid water on its surface. We know this from the mineral evidence left behind, from features that could only have been carved by flowing water, and from the presence of ancient riverbeds and lake basins that are now dry. The Perseverance rover has been operating in Jezero crater, which was once a lake fed by an ancient river delta. The rover has been collecting core samples from ancient lake sediments that may contain preserved evidence of ancient microbial life, or may contain absolutely nothing. We have not yet determined which. Those samples are intended to be returned to Earth by a future Mars sample return mission, where they can be analyzed with the full suite of laboratory equipment that cannot be miniaturized enough to fit on a rover. If those samples contain anything that even hints at biological activity, it will be the most important scientific discovery in human history. If they contain nothing, it will constrain our models of how life begins. The Martian atmosphere is thin, less than 1% of Earth's surface pressure, and composed primarily of carbon dioxide. It is cold. Average surface temperature is around minus 60 degrees Celsius, though it can briefly rise above freezing near the equator in summer. Dust storms on Mars are seasonal events that sometimes grow to cover the entire planet. Global dust storms can last for months, reducing sunlight at the surface enough to strand solar-powered vehicles indefinitely. The dust storm of 2018 was one such event. It ended the Opportunity rover mission, which had been operating for 14 years, by blocking enough sunlight to drain its solar panels. The rover was designed to last 90 days. It lasted nearly 15 years. Its final transmission, when the dust storm overwhelmed it, was interpreted by engineers to mean something like, "My battery is low and it is getting dark." Jupiter is the solar system's giant, the largest planet, the most massive planet, and in many ways the most powerful environment in the solar system short of the Sun itself. If you put all the other planets in the solar system together and added them up, Jupiter would still outweigh them combined, and then some. Its gravity is so strong that it has fundamentally shaped the architecture of the solar system around it, sweeping up debris that might otherwise form a second asteroid belt or bombard the inner planets, capturing comets into its own gravity and shepherding the orbits of smaller bodies for billions of years. There is a theory called the Grand Tack hypothesis, which proposes that Jupiter actually migrated inward toward the Sun in the early solar system, potentially reaching the current position of Mars before being pulled back outward by the gravitational interaction with Saturn, and in doing so sweeping up much of the material that would have formed a more massive Mars and delivering water-rich material to the early Earth. If Jupiter's early migration is real, then Jupiter may have played a direct role in making Earth habitable. The Great Red Spot on Jupiter, a storm that has been continuously observed for at least 350 years, is currently shrinking. It was once large enough to fit 3 Earths inside it. Now it fits roughly 1. Scientists are not entirely sure why. It may eventually dissipate entirely, becoming a feature that generations of people will have to be told existed once. The storm itself is a high-pressure system rotating counterclockwise, an anticlone, with wind speeds in the outer bands reaching several hundred kilometers per hour. The cloud tops of Jupiter are extraordinarily cold, But deeper in the atmosphere, temperatures rise. At great depths, the pressure becomes so extreme that hydrogen changes phase, transitioning from a gas to a liquid, then to a state called metallic hydrogen, where the pressure is high enough that hydrogen's electrons become free to flow, making the material electrically conductive. This vast interior ocean of metallic hydrogen, rotating with the planet, generates Jupiter's enormous magnetic field, which is roughly 20,000 times stronger than Earth's magnetic field, and extends so far into space that, if you could see it, it would appear several times larger than the full moon in the night sky from Earth. Jupiter's moon Io is the most volcanically active body in the solar system, driven by tidal forces from Jupiter that knead its interior like dough. Io has hundreds of active volcanoes and lava lakes, and plumes of sulfur dioxide gas erupt hundreds of kilometers above its surface. The heat from tidal flexing keeps its interior molten. In a sense, Io is caught in a perpetual geological violence that Earth can barely compete with during its most active periods. Io's surface is painted yellow, orange, red, and white, sulfur compounds in various states, constantly resurfaced by fresh lava flows. Older terrain is buried under new deposits so quickly that Io's surface is one of the youngest in the solar system. Beneath the icy shell of Europa, Jupiter's fourth largest moon, there is believed to be a global ocean of liquid water. The evidence is compelling. Magnetic field measurements by the Galileo spacecraft showed fluctuations consistent with a conducting fluid beneath the surface, and the surface itself is covered in crisscrossing cracks and ridges that strongly resemble the kind of features you would expect from an ice shell slowly being cracked and refrozen from below. The ocean is estimated to be between 80 and 170 kilometers deep, far deeper than any ocean on Earth. The total volume of water in Europa's ocean is thought to be twice that of all Earth's oceans combined. And in the dark of that ocean, deep beneath kilometers of ice, there may be hydrothermal vents, places where the seafloor leaks heat into the cold water, creating chemical gradients that on Earth reliably support entire ecosystems. Life, if it exists anywhere else in the solar system, may well exist in Europa's ocean. The Europa Clipper mission launched in October 2024 and is en route to the Jovian system to investigate. It will make dozens of close flybys of Europa, studying its surface and interior, sampling the plumes of water vapor that appear to be erupting from the surface, and building the most detailed picture yet of whether Europa could support life. Ganymede, the largest moon in the solar system, larger than the planet Mercury, has its own magnetosphere, which is unique among moons. It generates a bubble of magnetic field embedded within Jupiter's much larger magnetic field, creating a miniature magnetosphere with aurora rings near its poles. Europa, Ganymede, and Callisto are all suspected to have subsurface liquid water oceans, which means that of Jupiter's 4 Galilean moons, 3 may have internal oceans, 3 potentially habitable water worlds, orbiting a single planet in our own solar system. Saturn needs no dramatic setup. It is instantly recognizable and instinctively beautiful, even to people who know almost nothing about astronomy. But the reality of Saturn is, as always, stranger than the aesthetics suggest. Saturn is the least dense planet in the solar system. It is so light relative to its size, it is mostly hydrogen and helium, that if you could find a bathtub large enough, Saturn would float. The planet's density is about 68% that of water. The rings of Saturn are mostly water ice, particles ranging from microscopic grains to boulders the size of houses, spread out in a structure that is about 270,000 kilometers wide, but, in most places, less than 100 meters thick. The rings are astonishingly flat relative to their width. If you modeled Saturn's rings proportionally to the same scale as a sheet of paper, the sheet of paper would be wider than the space between the rings and their planet. And the rings are young. Not as young as a human generation, but young on geological and astronomical timescales. Multiple lines of evidence suggest the rings formed somewhere between 10 million and 100 million years ago. The solar system is 4.5 billion years old. The rings are a recent feature, cosmically speaking, and they are slowly disappearing. Ring rain, where charged water particles are drawn down into Saturn's atmosphere along magnetic field lines, is removing ring material at a rate that would eliminate the rings entirely within perhaps 300 million years. We exist in the window of time when Saturn has the rings we know. In 300 million years, if any astronomers exist, they will see a very different Saturn. Saturn's moon Titan is the only moon in the solar system with a thick atmosphere, and the only world other than Earth known to have stable bodies of liquid on its surface. But the liquid is not water. It is methane and ethane, pooled in lakes and seas near the poles, fed by methane rain that falls from orange-tinted clouds of nitrogen and complex organic chemicals. Titan's atmosphere is mostly nitrogen, like Earth's, and it is thick enough to produce a surface pressure about 1.5 times that of Earth. The surface is cold, around -179 degrees Celsius, and the sky is orange-brown from the photochemical smog that Titan continuously produces. Beneath the hydrocarbon haze, landscapes of ice bedrock and frozen water have been shaped by rivers and lakes of liquid methane. There may be a subsurface water ocean, making Titan a world with two completely different kinds of liquid: methane at the surface, water deep below. NASA's Dragonfly mission will land a rotorcraft on Titan, a drone, that will fly between multiple sites on Titan's surface, covering more ground than any previous planetary mission and investigating the chemistry of a prebiotic world. Enceladus, Saturn's sixth largest moon, was one of the biggest surprises in the history of planetary science. When the Cassini spacecraft flew through one of its plumes, geysers of water vapor erupting from cracks near the South Pole, it detected water, sodium, organic molecules, molecular hydrogen, and silica nanoparticles. Molecular hydrogen in particular was significant, because on Earth, molecular hydrogen dissolved in water near hydrothermal vents is a primary energy source for microorganisms called methanogens. The chemistry of Enceladus's plumes is consistent with active hydrothermal reactions happening at the bottom of its subsurface ocean. Enceladus is not just potentially habitable, it is actively expelling evidence of what might be a habitable environment into space, which means we could potentially sample it from orbit, or even confirm the presence of life without landing. Uranus and Neptune, the two ice giants, are substantially different from Jupiter and Saturn, and are underexplored. Uranus is unique among the planets in that its axial tilt is about 98 degrees, meaning it rotates on its side. Its poles point almost directly toward and away from the Sun during different seasons, creating the most extreme seasonal variation of any planet. During summer at one pole, the Sun circles overhead for 42 years. During winter, the pole sits in darkness for 42 years. One Uranian year is 84 Earth years. The cause of this extreme tilt is believed to be one or more giant impacts in the early solar system. Uranus also has the weakest internal heat emission of any planet. It radiates almost no more heat than it receives from the Sun, which is strange because Neptune, similar in composition and size, radiates about 2.5 times the heat it receives. What happened to Uranus's internal heat is unclear. Neptune, despite being the farthest major planet from the Sun, has the fastest wind speeds of any planet in the solar system. Winds in the Great Dark Spot, a storm system observed by Voyager 2 in 1989, which has since disappeared and been replaced by new storms, reached speeds of about 2,100 kilometers per hour. Neptune's wind speeds are counterintuitive. Farther from the Sun means less solar energy, and yet the winds are faster. The mechanism may involve the planet's internal heat, which drives atmospheric convection. Neptune's largest moon, Triton, orbits the planet backward, retrograde, which means it almost certainly did not form alongside Neptune but was captured from the Kuiper Belt. Triton is doomed. It is inside Neptune's Roche limit, meaning tidal forces are slowly pulling it apart. In about 3.5 billion years, Triton will either break apart into a ring system around Neptune or fall into the planet entirely. Beyond Neptune lies the Kuiper Belt, a vast region of icy bodies extending out to about 50 astronomical units from the Sun, and beyond that, the scattered disk, and then the hypothetical Oort cloud, a shell of cometary bodies that may extend 1/3 of the way to the nearest star. Pluto, which was reclassified as a dwarf planet in 2006, is the largest known Kuiper Belt object. The New Horizons spacecraft flew past Pluto in 2015 and revealed a world of stunning geological diversity, mountains of water ice rising 3,000 meters above the plains, a vast nitrogen ice sheet called Tombaugh Regio, shaped like a heart, possible evidence of past or present geological activity, driven by radiogenic heating or tidal forces from its large moon Charon. Pluto and Charon are tidally locked to each other. Each keeps the same face toward the other, meaning if you stood on the far side of Pluto from Charon, you would never see Charon in the sky at all. The two bodies orbit a common center of mass that lies outside Pluto itself, making them arguably a double dwarf planet system, rather than a planet and its moon. New Horizons is still traveling outward from the solar system, the fifth spacecraft to be placed on a trajectory that will eventually take it out of the solar system entirely. The other four are Pioneer 10, Pioneer 11, Voyager 1, and Voyager 2. Voyager 1 is now the most distant human-made object ever built. As of late 2024, it is over 22 billion kilometers from Earth. It crossed the heliopause, the boundary where the sun's solar wind is overpowered by the interstellar medium, in August 2012, making it the first human-made object to enter interstellar space. Its signal, traveling at the speed of light, still takes over 22 hours to reach Earth each way. It was launched in September 1977. It is still alive. It still sends data. Engineers at the Jet Propulsion Laboratory have had to find creative solutions to a faulty chip in its onboard computer system, solutions that involve sending commands and waiting nearly a full day to see if they worked, to keep the craft operational. Voyager 1's nuclear power source, a radioisotope thermoelectric generator, is slowly losing power and will eventually no longer supply enough electricity to run any of the spacecraft's instruments. When that happens, humanity's most distant ambassador will go silent, continuing its journey outward into the galaxy in complete silence, carrying a gold-plated record with sounds and images of Earth, on the infinitesimal chance that something, somewhere, someday finds it. The Voyager missions represent something about the human story in space that is worth pausing on, because the history of space exploration is not just a story of engineering. It is a story of decisions made by human beings under extraordinary pressure, with incomplete information and imperfect tools, who nevertheless pushed the boundaries of what we collectively thought was possible. The era of space exploration began not in the comfortable halls of government research facilities but in the shadow of World War II, driven forward by a geopolitical competition that used the cosmos as its battlefield. The rocket technology that launched the first satellites into orbit was not designed for exploration. It was designed for war. The V-2 rocket, developed in Germany under Wernher von Braun, was the world's first long-range ballistic missile, and the world's first rocket to cross the boundary of space. Von Braun himself was a member of the Nazi Party and the SS, and the V-2s were built with slave labor from concentration camps, a fact that is often glossed over in popular histories of the space age. After the war, both the United States and the Soviet Union scrambled to capture German rocket scientists and their technology. Von Braun and most of his team were taken to the United States under Operation Paperclip, where they eventually became central figures in the American space program. The man who put the first humans on the moon had previously helped build weapons that killed thousands of people and were produced by prisoners who worked and died in underground factories. That moral complexity sits underneath the entire early history of space exploration and does not go away simply because the subsequent achievements were genuinely inspiring. Both the American and Soviet programs in the late 1950s and 1960s were fueled by military strategic interest as much as scientific curiosity. ICBMs and space rockets are essentially the same technology. An ICBM is just a rocket that comes back down in a specific place. The satellite reconnaissance programs of both nations were conducted under cover of scientific missions. The first American reconnaissance satellite, Corona, was disguised publicly as a scientific program called Discoverer. The photographs it returned were retrieved by aircraft catching film canisters falling from orbit, and they revealed Soviet military installations with a clarity that transformed American military intelligence. Space, from the beginning, was not only about exploration, it was about power, but the human achievements were real. On October 4, 1957, the Soviet Union launched Sputnik 1, the first artificial satellite to orbit Earth. It was a polished aluminum sphere about 58 centimeters in diameter, weighing 83 kilograms, with 4 radio antennas that broadcast a simple radio beep. The beep could be heard by amateur radio operators around the world. It circled the Earth every 96 minutes. It was the first object built by human hands to orbit another world. Its launch triggered a crisis in the United States, which suddenly realized that the Soviets had a rocket capable of reaching orbit, and therefore capable of reaching anywhere on Earth. Congress passed the National Defense Education Act, massively increased funding for science and mathematics education, and accelerated the formation of what would become NASA, established in July 1958. Less than a month after Sputnik 1, the Soviets launched Sputnik 2, carrying the first living creature to orbit Earth, a dog named Laika. Laika was a stray found on the streets of Moscow. She was trained for the mission but was never intended to return. The technology to bring her back safely did not exist. She died from overheating a few hours after launch when the thermal control system failed, though Soviet officials did not admit this until decades later, instead claiming she survived for several days. When the reality became known, it generated significant controversy about the ethics of animal testing in space. Laika's capsule orbited Earth for 5 months before burning up in the atmosphere. Monuments to Laika exist in Russia. The Americans launched their first satellite, Explorer 1, in January 1958. It was a small, slender cylinder built by a team led by James Van Allen, and it carried a cosmic ray detector that made the first major scientific discovery of the space age: the Van Allen radiation belts, zones of high-energy particles trapped by Earth's magnetic field that circle the planet. This discovery was immediately useful for spacecraft design, since the radiation belts pose a significant hazard to electronics and astronauts passing through them. Yuri Gagarin became the first human being in space on April 12, 1961, completing one orbit of Earth in 108 minutes aboard Vostok 1. He ejected from the capsule at altitude and parachuted separately, a fact that was concealed at the time because international aviation rules required the pilot to land with the vehicle, and the Soviets wanted the record to be official. Gagarin's flight path took him over Africa and the southern Pacific. He saw the Earth from space for the first time and described it as beautiful, a blue sphere wrapped in a thin layer of atmosphere that looked impossibly fragile. When he returned, he was immediately famous in a way that almost no human being has been before or since, a symbol not of one country but of what the species was capable of. He died 7 years later in a routine training flight in a MiG-15, the cause of which has never been fully established. He was 34 years old. Less than a month after Gagarin's flight, Alan Shepard became the first American in space, completing a 15-minute suborbital flight that barely reached space before arcing back to a splashdown in the Atlantic. The contrast with Gagarin's orbital flight was stark and embarrassing for the American side. 3 weeks later, President John Kennedy stood before Congress and committed the United States to landing a man on the moon before the end of the decade. It was not a scientific commitment, it was a political one. Kennedy's advisors had told him that the Soviets would likely beat America in most near-term milestones in space. The one thing they might plausibly win was a lunar landing, and a lunar landing, with a human crew, was expensive, dramatic, and symbolic enough to matter in the Cold War propaganda battle. Kennedy chose the moon. What followed was the most ambitious peacetime engineering project in human history. At its peak in the mid-1960s, NASA employed roughly 400,000 people directly and through contractors. The Apollo program cost about $25 billion in 1960s money, roughly $280 billion in today's terms. It produced 17 Saturn V rockets, still the most powerful rockets ever flown, each standing 111 meters tall, weighing about 2.8 million kilograms at launch, producing a thrust at liftoff of about 35 million newtons. 5 of the Saturn V's first-stage engines would ignite simultaneously at launch, burning a combination of refined kerosene and liquid oxygen at a rate that consumed all of its propellant in about 2.5 minutes, throwing the rocket to a speed of about 8,000 kilometers per hour by the time the first stage was discarded. Apollo 1, the first crewed Apollo mission, never flew. On January 27, 1967, Gus Grissom, Ed White, and Roger Chaffee were sealed inside the capsule on the launch pad during a pre-launch test when a fire broke out in the oxygen-rich atmosphere. The hatch could not be opened from the inside in less than 90 seconds, the result of a design that prioritized preventing accidental opening during spaceflight over emergency evacuation on the ground. All 3 astronauts died within seconds from asphyxiation and thermal injuries. The loss forced a halt to the program, a comprehensive redesign of the capsule, and a congressional investigation that exposed significant safety and management problems within NASA's contractor culture. Grissom had been so concerned about the spacecraft's readiness that before the test he had taped a lemon to the outside of the simulator as a joke. He was one of the most experienced astronauts in the program, a veteran of Mercury and Gemini, and he had serious doubts about the capsule. He expressed them. He was not listened to in the ways that mattered. Apollo 8 was the mission that changed how humanity saw itself. In December 1968, Frank Borman, Jim Lovell, and Bill Anders became the first human beings to travel to another world, orbiting the moon 10 times. On Christmas Eve, Anders photographed the Earth rising above the lunar horizon, a photograph that became known as Earthrise, one of the most reproduced photographs in history, and one that arguably did more to launch the modern environmental movement than any political speech or scientific paper. Seeing Earth as a small, blue, fragile-looking marble hanging in the black void of space from 250,000 miles away, with no feature visible that matched any national boundary, changed something in the people who saw it. The astronauts read from the Book of Genesis during a live broadcast that was the most watched television program in history up to that point. Neil Armstrong and Buzz Aldrin landed on the moon on July 20, 1969. Armstrong stepped onto the surface at 10:56 p.m. EDT. His first words, "That's one small step for man, one giant leap for mankind," were intended to include A before man, but the article was either not spoken or lost in transmission. Armstrong always insisted he said a man. Audio analysis has been inconclusive. The landing itself had been far closer to failure than was publicly known at the time. The onboard guidance computer, with about 4 kilobytes of memory, began generating alarm codes during the descent. The 12:02 alarm indicated that the computer was overloaded with tasks and was prioritizing guidance over other functions. The team in mission control, led by flight controller Steve Bales, had just a few seconds to decide whether to abort or continue, a decision involving years of preparation and thousands of people. Bales said go. The alarm was safe to ignore. Armstrong had to override the autopilot and fly the lander manually at the last moment because the targeted landing site was covered in boulders. He flew over the boulder field and set down in a safer area with about 25 seconds of fuel remaining. 25 seconds. Michael Collins orbited the moon alone in the command module during the landing, the most alone any human being has ever been, separated not just from all other humans, but from all communication whenever he passed behind the moon. He had a mission plan and scientific work to do. He reported feeling content rather than lonely. When Armstrong and Aldrin returned to the lunar module and lifted off from the surface, Collins watched the tiny ascent stage rise toward him. He knew that if the rendezvous failed, if the docking did not work, he would return to Earth alone, and Armstrong and Aldrin would die on the moon. There was no rescue option. He had considered this. He had made his peace with it. 12 human beings walked on the moon between 1969 and 1972. The last to do so were Gene Cernan and Harrison Schmitt, who stepped off the lunar surface on December 14, 1972 during Apollo 17. No human being has returned to the moon since. Cernan was the last to leave, and he said, "We leave as we came, and God willing, as we shall return, with peace and hope for all mankind." It has been over 50 years. The sense of trajectory that the Apollo program created, that we were going somewhere, that the moon was a waypoint, dissipated remarkably quickly once the political motivation was gone. The Soviets had lost the moon race. The American public had moved on. Funding was cut. 3 planned Apollo missions were canceled. The last 3 Saturn V rockets ever built, rockets capable of reaching the moon, were displayed horizontally in museums, as monuments to something we once did and chose not to continue. The Soviet space program had its own parallel history of achievement and catastrophe, much of it concealed at the time. The Soviets placed the first woman in space, Valentina Tereshkova, in June 1963. They conducted the first spacewalk, Alexei Leonov, in March 1965, who nearly died when his spacesuit inflated and he could not re-enter the airlock until he bled some air from the suit, an improvisation that was not in any procedure. They developed the Soyuz spacecraft, which has now flown more missions than any other crewed spacecraft in history, and is still launching astronauts to the International Space Station after more than 50 years. But they also had the Nedelin catastrophe of 1960, in which a ballistic missile exploded on the launch pad while engineers were working on it during a rushed countdown, killing an estimated 150 people, including Strategic Rocket Forces Marshal Mitrofan Nedelin. This was covered up until after the Soviet Union collapsed. The Soyuz 1 mission in 1967 killed cosmonaut Vladimir Komarov when his parachutes failed on re-entry, a mission that Komarov reportedly knew was dangerous but flew anyway because, as the story goes, if he refused, Yuri Gagarin would have been the backup and Komarov was not willing to send his friend to die. Whether the details of that story are entirely accurate is debated, but what is not debated is that the spacecraft was critically flawed and flew anyway. The Space Shuttle program, which ran from 1981 to 2011, was in many ways the defining chapter of American spaceflight for an entire generation. The shuttle was a revolutionary vehicle, reusable, capable of carrying large payloads to orbit, equipped with a robotic arm and a pressurized cargo bay, able to return equipment from orbit, serve as a platform for satellite repair and scientific experiments. It launched the Hubble Space Telescope, which has arguably produced more scientific return than any other instrument in the history of astronomy. It built the International Space Station, which has been continuously inhabited since November 2000, making it the longest continuously inhabited human structure off the surface of Earth. But the shuttle also lost 2 of its 5 orbiters to catastrophic failures. Challenger was destroyed on January 28, 1986, 73 seconds after launch, when an O-ring in one of the solid rocket boosters failed in unusually cold temperatures. The O-ring failure allowed hot combustion gases to breach the joint and ignite the external fuel tank. The orbiter broke apart at an altitude of about 15 kilometers. All 7 crew members, including Krista McAuliffe, a schoolteacher selected through a public competition to fly as the first citizen in space, died. The failure was caused not by a lack of knowledge. Engineers at Morton Thiokol had warned the night before launch that O-rings had shown concerning behavior at cold temperatures and that the launch should be delayed. Their concerns were overruled by managers under pressure from NASA leadership, who did not want another delay. The Presidential Rogers Commission that investigated the accident produced one of the most quoted passages in the history of engineering investigation, and it also, memorably, included physicist Richard Feynman, who demonstrated the O-ring failure by placing a piece of O-ring material in a glass of ice water during a televised session. The material lost its resilience at low temperatures. The cause was obvious. It had been known. The warnings had been issued. The system had failed not in the rocket, but in the decision-making process. Columbia was destroyed on February 1, 2003 during re-entry. The cause was a piece of insulating foam that broke off from the external tank during launch and struck the leading edge of the left wing, creating a hole in the thermal protection system. During re-entry, superheated plasma entered through the breach and destroyed the wing from the inside. The Columbia broke apart over Texas and Louisiana. All 7 crew members died. Again, the concern had been raised during the mission. Engineers worried about the foam strike and asked for reconnaissance imagery of the wing to assess the damage. Their requests were turned down. The assumption was that if damage had occurred, nothing could be done about it. There was no repair capability, no rescue option. That assumption turned out to be wrong. A subsequent analysis found that, had the damage been identified, a spacewalk repair using materials on board was potentially feasible. Or alternatively, the crew could have been rescued by a second shuttle launch before their consumables ran out. They were not given the chance. The pattern across both shuttle disasters and across Apollo 1 is the same. The technical warning existed. The people closest to the danger knew something was wrong. The organizational and political pressures of large institutions operating under schedule constraints and public expectations overrode the concerns of the engineers and scientists. This is not unique to space. It is a pattern documented in organizational disasters across industries, but space makes it vivid and irreversible. After the shuttle retired in 2011, the United States went through a period of dependence on Russian Soyuz capsules to reach the International Space Station, paying tens of millions of dollars per seat. The rise of commercial spaceflight has changed that landscape. SpaceX's Dragon capsule, developed under NASA's Commercial Crew Program, began carrying astronauts to the ISS in 2020. The Falcon 9 rocket, with its reusable first stage that lands itself upright on drone ships in the ocean, has transformed the economics of launch, dramatically reducing the cost per kilogram to orbit and enabling a new era of constellation satellites, commercial stations, and private missions. The Starship vehicle, still in development as of 2024, is designed to be the largest and most powerful rocket ever flown, taller than the Saturn V, designed for full and rapid reusability, and intended for lunar and eventually Martian missions. Blue Origin, founded by Jeff Bezos, launched its New Shepard vehicle on suborbital hops and is developing the New Glenn orbital rocket. Virgin Galactic briefly flew tourism missions on its Spaceship Two vehicle. The commercial space era has produced extraordinary results alongside tragedies. Virgin Galactic's Spaceship Two broke apart during a 2014 test flight, killing the co-pilot when it was determined the feathering mechanism was unlocked early. Across the era of human spaceflight, approximately 600 people have been to space as of 2024. Of those, only 12 have stood on another world. The vast majority have orbited Earth, some for a few minutes, some for record durations measured in months or years. The record for the longest continuous human spaceflight is held by cosmonaut Valery Polyakov, who spent 437 consecutive days aboard Mir, a record set in 1995 that has never been broken. The purpose of long-duration spaceflight records is largely the same as it has always been: to understand what extended exposure to microgravity and space radiation does to the human body, knowledge that will be essential for any mission to Mars, which would require roughly 7 months of travel each way, and potentially years on the surface. The effects of long-duration spaceflight on the human body are significant and in some cases alarming. Microgravity causes bone density to decrease. Without the constant mechanical loading that gravity provides, bone is resorbed faster than it is rebuilt, and astronauts on the ISS can lose 1 to 2% of bone mass per month in the most affected regions. Muscles atrophy. The cardiovascular system adapts to the redistribution of fluids toward the head, which also causes a phenomenon called visual impairment and intracranial pressure syndrome, where the elevated fluid pressure in the skull flattens the back of the eye and compresses the optic nerve, leading to degraded vision that in some astronauts has not fully recovered after return. The immune system is suppressed. Radiation exposure in low Earth orbit is roughly equivalent to having a chest X-ray every day, and on a Mars mission traveling outside Earth's magnetosphere, it would be significantly higher, one of the primary engineering challenges for any crewed deep space mission. The radiation environment of deep space is shaped by two sources: galactic cosmic rays, which are high-energy particles from outside the solar system and are extremely difficult to shield against without impractical masses of shielding material, and solar particle events, sudden bursts of high-energy protons from solar flares and coronal mass ejections that can be partially anticipated and partially shielded. The total radiation dose for a Mars mission is estimated at roughly 1 sievert, which corresponds to a 5% increased lifetime risk of cancer, above the current NASA career limits for astronauts in low Earth orbit. This will require either new shielding technologies, pharmacological countermeasures, faster transit times, or simply a higher accepted risk tolerance for the people who go. The International Space Station itself is an extraordinary achievement that is often taken for granted, partly because it has become routine. It orbits at an altitude of roughly 400 kilometers, circling Earth about 16 times a day, at a speed of roughly 27,700 kilometers per hour. If you are patient, you can see it cross the sky as a bright, fast-moving point of light on any clear night. Inside, crews of up to 8 people work in a pressurized volume about the size of a 6-bedroom house, spread across multiple connected modules contributed by the United States, Russia, Europe, Japan, and Canada. The ISS has hosted science experiments on everything from protein crystallization to burning flames in microgravity, which are spherical, with no convection to elongate them, to the behavior of water and other fluids without gravity to organize them. It has been used to study Earth from orbit, to test systems for deep space missions, and to develop the medical and biological knowledge needed to keep people alive and functional in space for longer durations. The future of the ISS is uncertain. NASA intends to deorbit the station in 2030, guiding it into the South Pacific in a controlled re-entry. Russia's participation has been complicated by geopolitical events following its invasion of Ukraine in 2022, which strained space cooperation in ways that have not fully resolved. Commercial successors are in development. Axiom Space has modules in production that will eventually attach to the ISS and then separate to form an independent commercial station. And several other companies are proposing station concepts, but none of them have been built yet. The period between the end of the ISS and the establishment of a successor station represents a risk of losing the continuous human presence in low Earth orbit that has been maintained since 2000. Beyond Earth orbit, the next major goal for human spaceflight is the Moon, followed, perhaps in the late 2030s or 2040s, by Mars. The Artemis program, NASA's return to the Moon, aims to land the first woman and the first person of color on the lunar surface, establishing a sustainable presence that includes a gateway orbital station around the Moon as a staging point for surface missions. The first Artemis mission flew in November 2022, sending the Orion capsule around the Moon on an uncrewed test. The crewed lunar flyby and eventually the landing are planned for subsequent missions, though schedules in spaceflight have a long history of slipping. The Moon itself holds potential resources that make it interesting beyond pure science. Water ice deposits in permanently shadowed craters near the lunar poles, confirmed by multiple observations including by the L-Cross impact mission, which deliberately crashed a rocket stage into a shadowed crater and analyzed the resulting plume, could be used for drinking water, agricultural water, or split into hydrogen and oxygen for rocket propellant. In situ resource utilization, ISRU, Using materials found on-site rather than hauling everything from Earth is considered essential for any long-term lunar presence or deep space exploration. The Moon also contains helium-3, a potential fuel for certain types of nuclear fusion reactors that would produce less radioactive waste than conventional fusion, though the fusion technology to use it does not yet exist commercially. Let us now go back to the deep universe, because the story of how galaxies form and change over time is one of the most visually stunning and scientifically rich topics in all of astronomy. The Hubble Space Telescope changed our understanding of galaxy evolution by looking at the universe's history directly. Because light travels at a finite speed, looking across vast distances means looking back in time. When you observe a galaxy 10 billion light-years away, you are seeing it as it was 10 billion years ago, when the universe was less than 4 billion years old, still forming its first large structures. The Hubble Deep Field, captured in 1995 by pointing Hubble at a small, apparently empty region of sky for 10 consecutive days, revealed thousands of galaxies, some fully formed spirals like the Milky Way, others irregular, colliding, or in the process of assembly. Almost every point of light in that image is an entire galaxy, containing hundreds of billions of stars. That tiny patch of sky represents 1/24 millionth of the total celestial sphere. The implication is that the observable universe contains at least 2 trillion galaxies, more than previously estimated by an order of magnitude. Galaxy formation begins with dark matter. In the early universe, quantum fluctuations in the density of matter, fluctuations that were seeded in the first fractions of a second after the Big Bang during a period called inflation, grew over time as gravity amplified them. Dark matter, not coupled to the radiation field in the early universe the way ordinary matter was, could begin clumping earlier, forming halos that became the gravitational scaffolding into which ordinary matter eventually fell. Gas cooled inside dark matter halos, became denser, and eventually reached the conditions needed to form the first stars. The first stars, called population 3 stars, are thought to have been extraordinarily massive, hundreds of times the mass of our Sun, and extremely short-lived. They produced no elements heavier than helium in their cores during hydrogen burning, but their explosive deaths, and they would have been the most energetic supernovae ever, seeded the surrounding gas with heavier elements for the first time. No population 3 stars have ever been directly observed. They all died billions of years ago, but their signatures may be detectable in the composition of the most ancient surviving stars, and possibly in future observations with the James Webb Space Telescope. The James Webb Space Telescope, launched on December 25, 2021, represents the most significant advance in observational astronomy since Hubble, with a primary mirror 6.5 meters across, far larger than Hubble's 2.4 meters, and optimized for infrared wavelengths. Webb can see farther back in time than any previous telescope, observing galaxies as they were only a few 100 million years after the Big Bang. What Webb has found in its first years of operation has upended several existing models of galaxy formation. Galaxies in the early universe are more massive, more structured, and more numerous than models predicted. This is not a crisis. The models will be adjusted, but it is a reminder that the universe has a way of being stranger and richer than even our best theories prepare us for. Webb has also studied the atmospheres of exoplanets in unprecedented detail, searched for signs of carbon dioxide and water vapor in planetary atmospheres around other stars, and observed objects throughout the solar system including Neptune's rings, Titan's atmosphere, and the surface of Jupiter's moons. Its observations of nearby galaxies have resolved individual stars in systems far beyond what was possible before, enabling new measurements of distances and the expansion rate of the universe. The expansion rate of the universe, expressed as the Hubble constant, is currently one of the most contested measurements in cosmology. Two methods of measuring it give significantly different answers. Measurements based on the cosmic microwave background radiation, the afterglow of the Big Bang itself, give a value of about 67 kilometers per second per megaparsec. Measurements based on the distances to nearby Cepheid variable stars and Type 1a supernovae in the late universe give a value of about 73 kilometers per second per megaparsec. This discrepancy, called the Hubble tension, has grown more significant as both methods have been refined. It is not a measurement error. If it is real, it may require new physics, perhaps dark energy that changes over time, or a new relativistic species of particle, or something else entirely. Webb has been used to independently check the Cepheid calibration and has confirmed the higher value deepening the tension. This is one of the most live and important problems in contemporary cosmology. The cosmic microwave background, The CMB is itself one of the most remarkable things we can observe. It is the light released when the universe, about 380,000 years after the Big Bang, cooled enough that electrons and protons could combine into neutral hydrogen atoms for the first time. Before this moment, the universe was a hot, opaque plasma, and light could not travel freely. The moment neutral atoms formed, an event called recombination, the universe became transparent, and the light that had been trapped in the plasma flooded outward. That light has been traveling ever since, and we detect it today as a faint microwave glow coming equally from all directions, with a temperature of about 2.7 Kelvin. It is the oldest light we can detect. It was emitted when the universe was 1,000th of its current size, and in its tiny temperature fluctuations, variations of 1 part in 100,000s, are encoded the seeds of every structure in the universe, every galaxy, every cluster, every filament of the cosmic web. The maps of the CMB produced by the COBE-W map and Planck satellites show these fluctuations in exquisite detail and have produced some of the most precise measurements of cosmological parameters ever made. The age of the universe, its composition, the flatness of its geometry, the amplitude of the primordial fluctuations, the Big Bang itself, the event from which all of this emerged, is the subject of one of the most commonly misunderstood phrases in science. The Big Bang was not an explosion in space. It was an expansion of space. There was no center from which it burst outward. Every point in the universe was the center. The Big Bang happened everywhere simultaneously. Space itself began to expand, and matter and energy, which came into being along with space and time, expanded with it. In the first tiny fractions of a second, a period called inflation stretched the universe from a size smaller than a proton to roughly the size of a grapefruit in an unimaginably brief time, expanding by a factor of at least 10 to the 26th power. This rapid expansion smoothed out the universe, making it approximately uniform in temperature and density, while also stretching quantum fluctuations to cosmic scales, seeding the structure we see today. Inflation is very well supported by observations, the flatness of the universe's geometry, the uniformity of the CMB, the specific pattern of fluctuations, but the detailed physics of inflation and what drove it remain areas of active theoretical research. The question of what came before the Big Bang, or whether before is even a meaningful concept if time itself began at the Big Bang, is one that science cannot currently answer. Various proposals exist. The cyclic universe model, in which Big Bangs are periodically triggered by the collision of higher dimensional structures called branes. The eternal inflation model, in which our Big Bang is one of an infinite number of Big Bangs occurring in an infinite inflating spacetime. The Hartle-Hawking no-boundary proposal, in which time becomes imaginary at the Big Bang and the concept of a beginning dissolves. And the loop quantum cosmology model, in which the Big Bang was preceded by a contracting phase that bounced into expansion. None of these can currently be tested observationally. The question of what preceded the Big Bang may be fundamentally unanswerable with physical observations, not because we lack the technology, but because the Big Bang was the origin of the physical reality that observations can probe. The fate of the universe is better constrained than its origin, given what we know about dark energy. If dark energy remains constant, as the simplest version, Einstein's cosmological constant, predicts, the universe will expand forever, growing colder and more dilute. Galaxies within the local group, bound together by their mutual gravity, will eventually merge into a single giant elliptical galaxy in tens of billions of years. Our own Milky Way is already on a collision course with the Andromeda Galaxy. The two galaxies will begin to interact in about 4 to 5 billion years, and the full merger will take perhaps 2 billion years more. The collision is not the kind of apocalyptic event it sounds like. Stars are so far apart that even in a galaxy merger, stellar collisions are extremely rare. What will happen is a grand gravitational reshuffling. Both galaxies' spiral arms will be disrupted. Long streamers of stars will be flung outward, and after a period of violent interaction, the two will settle into a merged, roughly elliptical galaxy that astronomers have already given a name, Milkomeda. Our Sun, depending on its orbital history during the merger, might end up anywhere in the merged galaxy. Beyond Milkomeda, in the deep future, tens of billions of years from now, the accelerating expansion of the universe will carry distant galaxies beyond our cosmological horizon, the point past which light can no longer reach us because those regions are receding faster than light. This is not a violation of relativity. Nothing moves faster than light through space, but space itself can expand at any rate. As this happens, the observable universe available to any future civilization will shrink. Trillions of years from now, all galaxies outside the local group will be invisible, their light redshifted to undetectability, their existence erased from the observable sky. A civilization arising that far in the future might look out at a dark, empty cosmos and conclude, wrongly, that the universe contains only their local group, not knowing that hundreds of billions of other galaxies lie beyond the horizon, unreachable and invisible. The cosmological information available to any observer decreases with time. We are lucky, in a sense, to exist now, in the window when the universe's structure is still visible, when the CMB still exists, when we can still see back to the beginning. Eventually, and this is a timescale so vast that it borders on the metaphysical, all stars will exhaust their fuel. The most massive stars burn for only millions of years. Stars like our Sun burn for about 10 billion years. The smallest red dwarf stars burn so slowly that some of them will remain lit for 10 to 100 trillion years, 10,000 times the current age of the universe. But they too will eventually exhaust their hydrogen. When the last star dies, the universe will enter what cosmologists call the degenerate era, a cold, dark cosmos populated by white dwarfs, neutron stars, black holes, and planets orphaned from their dead stars, cooling slowly toward absolute zero over timescales measured in numbers with dozens of zeros. White dwarfs, given enough time, vastly more time than the universe has currently existed, will cool into black dwarfs, cold, dark, crystalline objects that glow with no light at all. Black dwarfs do not yet exist. The universe has not been around long enough for any white dwarf to have cooled that far. Beyond the degenerate era lies the black hole era, during which only black holes remain. And they too, over the unimaginable span of Hawking evaporation, will eventually disappear. The most massive black holes will take perhaps 10 to the 101st power years to fully evaporate, releasing their final burst of Hawking radiation as a small explosion of high-energy particles. After that, the universe enters what some call the dark era, a state of maximum entropy, diffuse and cold, containing only low-energy photons, neutrinos, and perhaps the decay products of protons, if protons are not in fact stable, but decay on timescales of around 10 to the 34th power years. In the dark era, nothing happens forever. Every thermodynamic gradient has been exhausted. No more information can be processed. The universe reaches a state called heat death. Maximum entropy, no usable energy, no further change. This is the most likely ultimate fate of the universe if dark energy remains constant. And yet, there is a concept called the Boltzmann brain that haunts this picture. In a universe at maximum entropy, quantum fluctuations still occur. Given enough time measured in numbers that have no meaningful expression in human language, random fluctuations could, in principle, spontaneously assemble a functioning brain, complete with false memories of a lifetime, that experiences exactly one moment of consciousness before dissolving back into the void. Such an observer, a Boltzmann brain, is a deeply troubling thought experiment, because if the universe lasts long enough in a thermal equilibrium state, Boltzmann brains might vastly outnumber ordinary observers who evolved through biological processes. This matters philosophically because some cosmological models predict conditions under which Boltzmann brains would be more common than ordinary observers, which would mean that for any given conscious observer, it is more likely they are a Boltzmann brain than a normal biological mind. If that logic is correct, then most experiences, including this one, would be disconnected illusions. Cosmologists take Boltzmann brain overproduction seriously as a constraint on physical models. Any model that predicts a Boltzmann brain-dominated future is considered suspect. Let us come back to something more grounded. The extraordinary weirdness of actual objects in the universe that we have observed, measured, and cataloged, because there are things out there so strange that no amount of theoretical preparation quite prepares you for them. Magnetars are a subtype of neutron star with magnetic fields so extreme they make ordinary neutron stars look moderate. The magnetic field of a magnetar can reach 10 to the 11th power Tesla, that is 100 billion Tesla. Earth's magnetic field is about 50 millionths of a Tesla. A magnetar's magnetic field is so strong that if one were as close to you as the moon, it would strip the iron from your hemoglobin before any other effect had time to matter. Magnetars produce starquakes, cracking of the rigid neutron star crust that release enormous bursts of gamma rays. On December 27, 2004, a magnetar called SGR 180620 produced a burst of gamma rays that, despite being 50,000 light-years away, was powerful enough to partially ionize the upper atmosphere of Earth. It was the most energetic event ever observed in our galaxy from an external source. Astronomers around the world who were using X-ray satellites at the time had their instruments temporarily blinded by the flash. If this magnetar were 10 light-years away, still far outside our solar system, but in the cosmic neighborhood, the burst would have triggered a mass extinction on Earth. Quasars are the most luminous, continuous objects in the known universe. They are the active galactic nuclei of young, distant galaxies, supermassive black holes actively consuming enormous quantities of gas and dust, their accretion disks blazing with radiation so intense that a single quasar can outshine an entire galaxy of hundreds of billions of stars by a factor of hundreds or thousands. The most luminous quasar known, J05294351, discovered in 2024, has a luminosity equivalent to about 500 trillion suns. It is powered by a black hole accreting at a rate of about 370 solar masses per year. These are not steady-state objects. The quasar phase represents a specific, intense period in a galaxy's history when the central black hole is growing rapidly. Most quasars existed in the early universe, roughly 10 to 12 billion years ago, when gas was more abundant and galaxy mergers more frequent. The Milky Way's own black hole, Sagittarius A star, likely went through a quasar phase billions of years ago. It has now settled into relative quiescence, like most central black holes in mature galaxies. Gravitational waves, ripples in the fabric of space-time itself, were predicted by Einstein in 1916 and finally detected directly for the first time on September 14, 2015, by the LIGO Observatory. The event, called GW 150914, was the merger of two black holes roughly 36 and 29 solar masses, located about 1.3 billion light-years away. The merger released more energy in gravitational waves than the combined luminosity of all the stars in the observable universe, not over their entire lifetimes, but in the roughly 0.2 of a second the merger lasted. The gravitational wave that reached Earth was a distortion of spacetime that stretched and compressed the 4-kilometer arms of the LIGO detector by a distance of about 1,000th the diameter of a proton. 1,000th of a proton. And the instrument detected it. The precision required to do this is beyond any mundane analogy. It represents the most sensitive measurement ever made by a human-built instrument. Since 2015, LIGO and its partner detectors, Virgo in Italy, Kagura in Japan, have detected dozens of gravitational wave events. Most are binary black hole mergers, but some are binary neutron star mergers, which are particularly exciting because they are also visible in light, producing short gamma-ray bursts and kilonovae, which are optical and infrared transients caused by the radioactive decay of heavy elements freshly synthesized in the merger. The first binary neutron star merger detected in gravitational waves, GW170817, was simultaneously observed across the electromagnetic spectrum from gamma rays to radio, representing the birth of multi-messenger astronomy, studying the universe simultaneously in gravitational waves and light. The kilonova produced in GW 170817 synthesized gold, platinum, uranium, and other heavy A process elements in quantities equal to several Earth masses, confirming that neutron star mergers are a primary source of many of the heaviest elements in the universe. The search for exoplanets, planets orbiting other stars, has transformed from a speculative endeavor into a field with over 5,000 confirmed discoveries as of 2024, and many thousands more candidates. The techniques used to find them are indirect. Most are detected either by the transit method, in which a planet crossing in front of its star causes a tiny periodic dimming of the star's light, detectable by precise photometry, or by the radial velocity method, in which the gravitational tug of the planet causes the star to wobble slightly, shifting its spectral lines in a periodic pattern. The Kepler Space Telescope, launched in 2009 and operating until 2018, discovered the majority of known exoplanets using the transit method, staring at a fixed field of roughly 150,000 stars simultaneously and searching for periodic dips in brightness. The sheer number of planets Kepler found, over 2,700 confirmed, established that planets are extraordinarily common in the universe. On average, every star in the Milky Way has at least one planet, likely more. The diversity of exoplanets discovered is staggering. There are hot Jupiters, gas giant planets in orbits so close to their stars that their years last only days, their dayside temperatures reaching thousands of degrees. There are super-Earths, rocky or water worlds larger than Earth but smaller than Neptune, with no analog in our own solar system. There are mini-Neptunes, ocean worlds, lava worlds, and puffy gas giants so diffuse they have densities lower than that of styrofoam. There are planets in binary star systems, circumbinary planets orbiting both stars with twin suns rising over their surfaces like a science fiction landscape. There are planets in wide triple star systems. There are planets with extreme orbital eccentricities, swinging from baking heat to deep freeze in a single orbit. There are tidally locked planets, like many of those orbiting the small red dwarf stars that make up about 70% of all stars, where one hemisphere permanently faces the star and the other faces away, creating a world divided between a scorching day side and a frozen night side, with potentially habitable conditions near the terminator line between them. The TRAPPIST-1 system, discovered in 2017, is one of the most remarkable planetary systems known. A tiny red dwarf star, barely larger than Jupiter, hosts 7 rocky planets in closely spaced orbits, 3 of them in the habitable zone where liquid water could potentially exist on the surface. All 7 planets are roughly Earth-sized. All 7 have masses that could support rocky terrestrial interiors. TRAPPIST-1e is currently considered one of the most potentially habitable worlds known. It receives a similar amount of energy from its star as Earth receives from the Sun. It is rocky, and it is close enough for future observations of its atmosphere. But the star is a red dwarf, which means it produces frequent, powerful flares that could strip the atmospheres of close-in planets over geological timescales. Whether TRAPPIST-1e has an atmosphere, and what that atmosphere contains, is one of the central questions that the James Webb Space Telescope has been working to answer through careful spectroscopic observations of transits. The question of life elsewhere in the universe connects to one of the most famous unsolved problems in science, the Fermi paradox. In 1950, physicist Enrico Fermi asked a simple question during a lunch conversation. If intelligent life is common in the universe, where is everybody? The galaxy is roughly 13 billion years old. Civilizations that arose a billion years before us would have had time to spread across the entire Milky Way, even at modest sublight speeds, and yet we see no evidence of any extraterrestrial civilization. No signals, no megastructures, no von Neumann probes, nothing. This is the Fermi paradox, and it has generated an enormous variety of proposed resolutions. Perhaps life is far rarer than we think. Maybe the emergence of life, or of complex multicellular life, or of intelligence, involves one or more steps that are extraordinarily improbable. Perhaps intelligent civilizations inevitably destroy themselves before reaching the capability to spread into the galaxy. Perhaps they avoid detection, for reasons we cannot guess. Perhaps the universe is young enough that we are among the first, and the silence is simply because no one else is old enough yet. Perhaps the distances are simply too great and the galaxy is not full of active signals. Perhaps, and this is the most disquieting possibility of all, the answer involves what is called the Great Filter, some barrier that civilizations do not typically survive. And the question of whether the Great Filter is ahead of us or behind us is one with existential implications. If the Great Filter is behind us, if the emergence of life or of complex cellular organisms or of intelligence is the barrier that almost nothing survives, then we might truly be alone, or nearly alone, in the observable universe, and the silence around us is the silence of a universe that never made it past the barrier that we did. In that case, our existence is a miracle of improbability, and our responsibility to survive and expand into the cosmos is staggering. If, on the other hand, the Great Filter is ahead of us, if it is something that civilizations reliably encounter after reaching technological capability, then the silence is a warning. We might be approaching something. Some transition, some capability, perhaps artificial intelligence, perhaps bioweapons, perhaps climate change, perhaps nuclear war, that ends civilizations before they can fill the galaxy. In that case, the silence is not reassuring, it is a pattern, and we are following the pattern. The search for extraterrestrial intelligence, SETI, has been ongoing since 1960 when Frank Drake pointed a radio telescope at the nearby stars Tau Ceti and Epsilon Eridani and listened. He heard nothing. In 1977, a candidate signal called the WOW signal was detected by the Big Ear radio telescope at Ohio State University, a strong narrowband signal from the direction of the constellation Sagittarius that lasted exactly 72 seconds before the telescope rotated past it. It has never been detected again. Its origin is unknown. The most recent analysis suggests it may have been a signal from a hydrogen cloud near a pair of comets, but the matter is not fully resolved. The WOW signal is the most anomalous signal ever detected in the history of SETI and remains intriguing precisely because it has no confirmed natural explanation. Modern SETI has expanded far beyond radio waves to include optical SETI, looking for laser pulses from other civilizations, and technosignature searches, looking for evidence of technological activity such as industrial pollution in a planet's atmosphere detectable in spectroscopy, waste heat from large-scale energy use, or anomalous dimming patterns that might indicate artificial structures around stars. The star KIC 8462852, also known as Tabby's star, attracted enormous attention in 2015 when citizen scientists analyzing Kepler data noticed that it dimmed in irregular, dramatic, asymmetric ways that no known natural phenomenon explained cleanly. The most dramatic proposed explanation was an alien megastructure, a Dyson sphere in construction perhaps. Follow-up observations found that the dimming was wavelength-dependent, with more dimming at shorter wavelengths, which is consistent with dust rather than solid opaque material. The current leading explanation involves a swarm of comets or dust from a disrupted body blocking the starlight intermittently. It is almost certainly not aliens, but the frenzy of attention it generated revealed something about human psychology in the face of anomaly and the deep desire to not be alone. Even if we are not looking for intelligent life, the evidence for microbial life beyond Earth is something that astronomers now genuinely consider plausible. The requirements for life as we know it, liquid water, a source of chemical energy, and organic molecules, are apparently not rare. Water ice has been found throughout the solar system, on the Moon, on Mars, on nearly every moon of the outer planets, in the asteroid belt, in comets. Organic molecules, the carbon-based chemistry that underlies biology, are abundant throughout the universe. They form in the cold, dense molecular clouds where stars are born, and they rain down on planets via comets and asteroids. The discovery that amino acids, the building blocks of proteins, are present in meteorites confirmed that biology's raw materials are not unique to Earth. The question is whether liquid water and chemical energy in the same place at the same time, over geological timescales, is sufficient to begin life, or whether something more is required. The origin of life on Earth, abiogenesis, remains one of the deepest unsolved problems in biology. We do not know how the first self-replicating molecules arose from prebiotic chemistry. We know that life on Earth appears to have begun very quickly, within perhaps 500 million years of Earth's formation, in a period called the Late Hadean, when the planet was still being heavily bombarded by asteroids. Life may have begun multiple times and been wiped out before it stuck. Life may have begun in hydrothermal vents on the seafloor, as some models suggest, where chemical gradients between alkaline vent fluids and the acidic early ocean could drive chemistry analogous to what cells do with membranes and proton gradients. Or life may have begun in warm little ponds at the surface, as Darwin famously speculated, where cycles of wetting and drying could concentrate and polymerize organic molecules. Or somewhere else entirely. The chemistry is rich and the experiments are ongoing. What we know is that once life began on Earth, it proved extraordinarily resilient and creative. And in 4 billion years of evolution, it produced one species, us, capable of looking back at the cosmos that made it, and asking how all of this came to be. That is, if you pause and let it land fully, one of the most remarkable facts about the universe. The universe, through physics, chemistry, geology, and biology, over billions of years, produced creatures that study the universe. The cosmos became aware of itself, at least in this small corner, through the brains of organisms that evolved on a rocky planet in a corner of an unremarkable galaxy. Whether that has happened elsewhere, we do not know. Whether we are the only instance, we do not know. But it happened here, and that is not nothing. The study of the universe also has a way of revealing things about our position in time. We exist at a specific moment in cosmic history that is, in certain ways, uniquely good for the kind of cosmology we do. The CMB is still detectable. The universe's large-scale structure is still visible in all directions. The stars are in full production. The chemical enrichment of the universe with heavy elements has proceeded far enough that rocky planets can form and life can emerge, but not so far that the universe has grown old. We are neither too early. There were not enough heavy elements in the universe's first billion years for rocky planets to be common, nor too late. when all the stars will have dimmed and the observable universe shrunk to a local remnant. We are here in the middle chapter, when the universe is most interesting and most knowable. The night sky above your head contains something for each of those scales simultaneously. The moon, 250,000 miles away. The sun, 93 million miles away. Mars and Jupiter, hundreds of millions of miles away. Alpha Centauri, the nearest stellar system, 25 trillion miles away. The Andromeda Galaxy, 15 quintillion miles away, visible to the naked eye on a dark night as a faint smudge in Perseus. And beyond that, the universe stretching outward for 46 billion light-years in every direction, most of it invisible to us without instruments, most of it unreachable even at the speed of light, all of it real, all of it there. There are approximately 10,000 stars visible to the naked eye from Earth across the entire celestial sphere, under ideal dark sky conditions. The Milky Way contains between 200 and 400 billion stars. The observable universe contains roughly 2 trillion galaxies. The number of stars in the observable universe is estimated at around 2 times 10 to the 23rd power, approximately the same order of magnitude as the number of grains of sand on all of Earth's beaches, or the number of atoms in a few grams of any ordinary material. There are as many stars in the observable universe as there are atoms in your brain. Try to sit with that. It does not quite fit. But it is real. The solar system is approximately 4.5 billion years old, formed from a collapsing cloud of gas and dust that was itself the remnant of earlier stellar generations. The specific atoms in your body, the carbon, nitrogen, oxygen, calcium, iron, were synthesized in those earlier stars and scattered into space by their deaths. You are made of star remnants, not metaphorically, literally. The iron in your blood was forged in a dying star. The calcium in your bones was produced in supernovae. The oxygen you are breathing right now was synthesized in the nuclear fires of stars that lived and died before the sun existed. You are, in the most literal physical sense, a temporary local organization of stellar debris that is capable of contemplating its own origin. The pace at which new discoveries about the universe are accumulating has never been faster. The gravitational wave detectors are running continuously, catching dozens of events per year. Webb is producing data on thousands of galaxies and exoplanets. New wide-field surveys are mapping billions of objects across the sky. The Vera Rubin Observatory in Chile, designed to image the entire visible southern sky every few nights, will detect billions of objects over its 10-year survey, catching supernovae as they happen, tracking near-Earth asteroids, mapping the dark matter distribution through gravitational lensing, and searching for the hypothetical Planet 9, a distant, large planet beyond Neptune that some orbital anomalies of extreme Kuiper belt objects suggest might exist. If Planet 9 exists, it would likely be between 5 and 10 Earth masses, in an orbit thousands of astronomical units from the Sun. At that distance, it would take between 10,000 and 20,000 years to complete a single orbit. It has never been directly observed. The universe does not owe us comprehensibility. It does not owe us familiarity or comfort or answers. It will continue doing what it does, expanding, cooling, forming stars and black holes and galaxy clusters and gravitational waves, entirely indifferent to whether any of it makes sense to the small, warm creatures on one particular rocky planet who have been looking up at it with wonder and fear and instruments for a few thousand years. But those creatures keep looking. They build bigger telescopes. They send their machines to other worlds and eventually intend to go themselves. They listen for signals. They measure the light from the most distant galaxies. They model the first seconds of time. They ask questions that may never be answerable. And in doing all of this, they are doing something that, as far as we know, nothing else in the observable universe does. They are trying to understand it. There is something almost indescribable about that fact, if you let it be what it is. In a universe that is mostly dark matter and dark energy, things we cannot see or touch or understand. In a universe where the ordinary matter that makes up everything visible is a minority. In a universe where most planets are frozen or baked or crushed. Where most of space is vacuum. Where the distances between things are so vast that a signal traveling at the speed of light takes millions of years to cross between galaxies. In all of this, on one planet, for reasons still being worked out, life arose and eventually produced beings that look outward. That is the story of everything we have been talking about. And it is not finished. Not by a long way. The next 50 years of astronomy and space exploration will likely include the detection of an atmosphere around a potentially habitable exoplanet, possibly containing biosignature gases. They will include the return of human beings to the lunar surface. They may include the first robotic missions to the moons of the outer planets to search directly for life. They may include the first crewed mission to Mars. They will certainly include the detection of more gravitational wave events, more black hole mergers, possibly a neutron star merger close enough to be observed in extraordinary detail. They will include new data on dark matter from neutrino detectors and direct detection experiments. They will include new mapping of the large-scale structure of the universe and new precision measurements of the Hubble constant. They may, and this is where it gets really exciting, include something that genuinely surprises us, something we did not expect, something that requires a new theory, a new framework, a new way of thinking about what the universe is. That has happened before. It will happen again, because the universe is not done being strange. It has never been done being strange, and neither, it turns out, are we. Consider the star Eta Carinae for a moment. It is one of the most massive and luminous stars known to exist in the Milky Way, roughly 100 to 150 times the mass of our Sun, and about 5 million times more luminous. It sits about 7,500 light-years away in the constellation Carina. In 1843, it underwent what is called a great eruption, briefly becoming the second brightest star in the night sky, visible in full daylight before dimming back. The event was not a supernova. The star survived. But during those years, it expelled mass equivalent to several suns into a pair of lobes we can still observe today, a structure called the Homunculus Nebula. What triggered the eruption is still debated. What is not debated is what will happen eventually. Eta Carinae is unstable. It is living on borrowed time by stellar standards. When it does finally go supernova, possibly in the next 10,000 years, possibly in the next million, it will be visible in daylight from Earth. It may even produce a gamma-ray burst, a focused beam of high-energy radiation from its poles. Whether that beam points toward Earth is something we do not currently know. If it does, the consequences at 7,500 light-years of distance would be significant, but not civilization-ending. The ozone layer would be damaged on the hemisphere facing the burst. Radiation levels would increase. The effects would be measurable for years. This is not an imminent threat, but it is real. And it is there, and it has a name. Betelgeuse, the bright red star that marks the right shoulder of Orion, is another supernova candidate, perhaps the most famous one. It is about 700 light-years from Earth, making it close enough that if it went supernova, it would be spectacular, easily visible in daylight, casting shadows at night, and remaining as a bright, naked-eye object for weeks or months before fading. In late 2019 and early 2020, Betelgeuse dimmed dramatically and unexpectedly, dropping to a historically low brightness that sparked genuine excitement and wild speculation that it might be on the verge of exploding. The actual explanation turned out to be a massive outpouring of cool gas from the star's surface that condensed into dust, blocking some of its light, what astronomers called a great dimming event, essentially a giant cold splotch that dimmed one hemisphere of the star's surface. Betelgeuse has since recovered to normal brightness, but the episode was a reminder that red supergiant stars are inherently variable and complicated objects whose surfaces roil and churn in complex convective patterns, with single convective cells that might span the entire volume where our solar system would fit inside. Betelgeuse is old enough and massive enough, perhaps 15 to 20 times the mass of our Sun, that it has already fused hydrogen, then helium, and is now fusing heavier elements in nested shells around an iron core that cannot be fused further. Iron fusion absorbs energy rather than releasing it. The moment the iron core exceeds a critical mass, about 1.5 solar masses, nothing can stop the collapse. It will happen in an instant. A core that currently spans roughly the volume of Earth will collapse to a neutron star about 12 miles across in a fraction of a second. The outer layers will receive the shockwave of that collapse and be blasted outward in a supernova. Neutrinos, produced in enormous quantities during the neutron star formation, will carry away most of the energy of the collapse. About 10 to the 58 power neutrinos will stream outward in a pulse lasting roughly 10 seconds. A handful of them will pass through your body every second, even when the star is quiet. During a supernova at Betelgeuse's distance, your body would intercept billions of them in that 10-second burst. They would do nothing to you. They barely interact with ordinary matter at all. But the neutrino burst from a nearby supernova would arrive at Earth hours before the light, because the neutrinos escape immediately from the collapsing core while the optical light takes time to work its way out through the stellar envelope. This means if our neutrino detectors registered an anomalous burst, Astronomers would know a supernova was about to light up the sky before it visually appeared. A few hours of warning. We have done this once. On February 23, 1987, a supernova lit up in the Large Magellanic Cloud, a satellite galaxy of the Milky Way about 160,000 light-years away. It was the first naked-eye supernova visible since 1604, and it is known as SN 1987A. Crucially, detectors in Japan, the United States, and the Soviet Union detected a burst of 25 neutrinos in a window of about 13 seconds, roughly 3 hours before the optical brightening became visible. 25, from 160,000 light-years away, through the entire mass of Earth, 25 neutrinos were caught in detectors that happened to be running at the time. It was one of the most significant detections in the history of physics, the first detection of neutrinos from an astrophysical event, confirming the core collapse model of supernovae. The location of SN 1987A has continued to be monitored in the decades since. A neutron star should have formed at the center. We have not yet directly detected it. The dense cloud of debris obscures the core, but there are indirect hints of its existence in the X-ray and radio emissions from the remnant. Astronomers expect to see it clearly as the debris cloud thins over coming decades. The Large Magellanic Cloud and its companion, the Small Magellanic Cloud, are visible to the naked eye from the southern hemisphere, pale, cloud-like patches in the southern sky, each one an entire galaxy. The Large Magellanic Cloud contains roughly 30 billion stars and is currently in the process of being distorted by its gravitational interaction with the Milky Way. Contrary to what was long believed, the Magellanic Clouds are not permanent satellites of the Milky Way. Their velocity relative to the Milky Way suggests they may be on their first close pass, having been pulled in from farther away relatively recently. They will eventually be consumed by the Milky Way, their stars added to our galaxy's halo. The rate at which galaxies devour smaller companions is a normal feature of galaxy evolution. The Milky Way's halo, the diffuse, roughly spherical region surrounding the disk, contains dozens of stellar streams, the remains of dwarf galaxies and globular clusters that were gravitationally disrupted, and their stars scattered along great arcs across the sky. The Sagittarius stream is the most prominent, a band of stars that wraps almost completely around the sky, the remnants of the Sagittarius dwarf spheroidal galaxy that the Milky Way has been consuming for billions of years. The Milky Way has a long history as a cannibal. Globular clusters themselves, tightly packed spherical collections of hundreds of thousands to millions of very old stars, orbit the Milky Way in the halo region and are among the most ancient objects in the galaxy, many of them 13 billion years old, nearly as old as the universe itself. The stars inside globular clusters are so densely packed near the center that stellar encounters are common, and unusual stellar objects, blue stragglers for instance, which appear younger than their neighbors because they have merged with or accreted material from companion stars, are abundant. The cores of dense globular clusters may harbor intermediate mass black holes, in the range of hundreds to tens of thousands of solar masses, potentially representing a class of black holes that bridges the gap between stellar mass black holes and the supermassive variety. The evidence for intermediate mass black holes is still being assembled and debated, but several clusters show signs of a concentrated mass at their center that is too large to be explained by a collection of stellar remnants. Omega Centauri, the largest and most massive globular cluster associated with the Milky Way, is so large and complex, with multiple stellar populations of different ages and chemical compositions, that astronomers have suggested it may actually be the stripped core of a dwarf galaxy that was consumed by the Milky Way billions of years ago. Its supermassive core might harbor an intermediate mass black hole of about 40,000 solar masses. Omega Centauri is about 17,000 light-years away and contains roughly 10 million stars in a sphere about 150 light-years across. On a dark night in the southern hemisphere, it is visible to the naked eye as a fuzzy star, and through binoculars it is immediately resolved into a stunning ball of ancient suns. The ancient stars and globular clusters belong to what astronomers call population 2, stars with very low abundances of elements heavier than helium, formed from the nearly pristine gas of the early universe. The Sun is a population 1 star, metal-rich by astronomical standards, meaning it formed from gas that had already been enriched by multiple generations of earlier stars. The difference in heavy element abundance between population 1 and population 2 stars changes what is possible around them, Planet formation around population 1 stars is common because there is plenty of silicon, iron, carbon, and oxygen to build rocky worlds. Planet formation around population 2 stars is thought to be far rarer. If planetary systems do form around population 2 stars in globular clusters, they face an additional challenge. The extreme stellar density of the cluster means close gravitational encounters are common, and planetary systems can be destabilized over time by passing stars scattering planets into different orbits or ejecting them entirely. Rogue planets. Planets that have been ejected from their parent systems and now wander the interstellar medium without a host star are thought to be extraordinarily common. Estimates based on gravitational microlensing surveys and theoretical models suggest there could be billions of rogue planets in the Milky Way, some of them potentially as massive as Jupiter. A rogue Jupiter-mass planet, still warm from formation or from residual radioactive decay, might retain a thick hydrogen atmosphere and maintain subsurface conditions that, in the most speculative imaginings, could harbor some form of life sustained by geothermal heat rather than sunlight. Most rogue planets will be cold, dark, and lifeless, but the sheer number of them, and the possibility that some might have moons warmed by tidal forces, makes them a topic of genuine if speculative astrobiological interest. The concept of a habitable zone. The range of distances from a star where liquid water could exist on a planetary surface is a useful starting point, but the more we learn about the solar system and exoplanets, the more we realize habitability is more complex than distance. Europa is well outside the traditional habitable zone of the Sun, yet it almost certainly harbors a liquid water ocean. Enceladus is even farther. Titan's liquid methane lakes offer a completely different kind of potentially habitable environment that requires no liquid water at all. And on the other end, Venus is within the habitable zone of the Sun by some definitions, yet is thoroughly uninhabitable. The habitable zone is a useful concept for prioritizing targets in exoplanet surveys, but it is not the whole story of habitability. One factor that is increasingly recognized as important is stellar stability over geological timescales. Life on Earth required roughly 4 billion years to develop complex multicellular forms from the first simple cells. The star hosting a potentially inhabited world needs to be stable enough over that timescale to allow planetary conditions to be consistently permissive. Red dwarf stars, which are the most common type of star and which burn for tens to hundreds of trillions of years, might seem ideal on this basis, but in their youth they produce enormous flares far more frequently and intensely than the Sun, which could strip atmospheres and damage the chemistry of life before it has a chance to establish itself. Whether the planets of mature red dwarf stars can hold onto substantial atmospheres over billions of years, given that the planets must orbit very close to the dim star to receive enough warmth, is one of the central questions in exoplanet science today. The Sun itself has been remarkably stable over its history. Solar output has gradually increased over time. The young Sun was roughly 70% as luminous as it is today, yet life existed on Earth throughout. The early Earth must have been kept warm enough for liquid water through some combination of a different atmospheric composition, a stronger greenhouse effect, and possibly differences in cloud cover. This is called the faint young sun paradox, and it remains not fully resolved. The Sun's current activity cycle, the 11-year cycle of sunspot activity, solar flares, and coronal mass ejections, has significant effects on Earth's space environment and on the performance of GPS and communication satellites, on power grids, and on the Van Allen radiation belts. A particularly powerful solar storm in 1989 knocked out the power grid in Quebec for 9 hours. The Carrington event of 1859, the most powerful solar superstorm in recorded history, induced electrical currents so strong in telegraph lines that operators reported receiving shocks and continuing to send messages even after disconnecting their equipment from the power supply. If a Carrington-scale event struck Earth today, the damage to electrical infrastructure would be in the trillions of dollars and would take years to repair. This is a known risk, documented and studied, with mitigation strategies that are partially in place and partially not. The relationship between the Sun and Earth. The subtle ways in which the Sun's variability affects Earth's climate and technological infrastructure is just one of the many ways the universe impinges on daily life in ways that are easy to overlook. The Moon stabilizes Earth's axial tilt, preventing the wild oscillations in obliquity that Mars experiences, which Mars's tiny moons are insufficient to counteract. Without the Moon, Earth's axial tilt might wander between nearly 0 degrees and perhaps 85 degrees over millions of years, creating climate variations so extreme that the stability required for the long-term evolution of complex life would be undermined. Jupiter's gravity deflects a significant fraction of comets and asteroids that would otherwise have trajectories leading toward the inner solar system, though the protection is imperfect and Jupiter's influence can also redirect objects toward Earth. The probability that Earth sits in a relatively quiet region of the galaxy, far from the radiation environment of the galactic center, far from the dense star-forming regions where supernovae are common, may also be a prerequisite for complex life. The Milky Way is not uniform in its properties across its expanse. The galactic center, 30,000 light-years away, is a region of high stellar density, intense radiation, complex magnetic fields, and extreme dynamism, including the presence of Sagittarius A star, and dozens of other massive black holes. Life in the galactic center region, if it exists, would face a radiation environment far more hostile than anything in the solar system neighborhood. The spiral arms of the Milky Way, where stars are actively forming, are regions of turbulent star formation activity, supernova explosions, and intense radiation from massive young stars. Our solar system sits in a relatively quiet inter-arm region between the Orion and Sagittarius spiral arms, which is thought to be a safer environment for the long-term development of life. This is the galactic habitable zone concept, the idea that complex life may be most likely to develop in a specific annular region of the Milky Way, far enough from the galactic center to avoid extreme radiation and tidal disruption, close enough to benefit from the chemical enrichment of the interstellar medium that produces rocky planets. Our solar system sits within this galactic habitable zone. Whether that is a coincidence or a condition of our existence is a question without a clear answer yet. The story of cosmic rays offers another window into the way the universe reaches into our daily environment in invisible ways. Cosmic rays, high-energy particles, mostly protons and atomic nuclei, traveling at nearly the speed of light, constantly bombard Earth from all directions. Most originate within the Milky Way from supernova remnants and pulsar wind nebulae. Earth's magnetic field deflects lower-energy cosmic rays, but those that get through interact with the upper atmosphere to produce showers of secondary particles, muons, electrons, gamma rays, that rain down to the surface. At sea level, roughly 1 muon passes through your thumbnail every second. These particles carry enough energy to occasionally alter a DNA molecule in a cell, contributing a small but real background rate of mutation that drives evolution over geological timescales. The biosphere did not evolve in isolation from the cosmos. Cosmic radiation is part of the background against which life developed, and the mutation rate it helps produce is part of the mechanism of evolution. The universe participates in the shaping of life even on this small, obscure planet. When you step outside on a clear night and let your eyes adjust to the darkness, you are doing something that connects you to every human being who has ever lived. Every culture, every civilization, every person who has ever existed on this planet has done the same thing, looked up. The patterns they saw, the constellations, were different from culture to culture, but the stars were the same. The stars that form Orion were the same stars visible to ancient Babylonians who mapped them, to Polynesian navigators who used them to cross the Pacific, to Egyptian astronomers who aligned their temples with them, to the prehistoric people who painted animals on cave walls and presumably looked up at the same sky with the same wonder. The stars do not change on human timescales. The light you receive from Aldebaran tonight left that star 65 years ago. The light from Deneb left about 1400 years ago, when the Islamic Golden Age was producing breakthroughs in mathematics, chemistry, and astronomy that would eventually fuel the scientific revolution in Europe. The light from the Andromeda Galaxy left 2.5 million years ago, when our distant ancestors were making stone tools in Africa. It traveled all that way, through all that time, and tonight it enters your eye, and for a moment you are connected to a point 2.5 million light-years away. That is what space actually is. Not just equations and distances and temperatures and densities, though it is all of those things too, but a place that is connected to this one, a place that is reaching us, always in the form of light and neutrinos and gravitational waves and cosmic rays, carrying information about what is out there and what has happened and what the universe has been doing while we were here, living our lives on this small and improbable and extraordinary world. The work of understanding it is not finished. It will not be finished in our lifetimes or our children's lifetimes or any foreseeable lifetime, but it is the work. And it is worth doing, because the universe is real, and it is astonishing, and it is ours to know. Let us spend some time with the spacecraft that have gone where no human has, because their stories deserve more than footnotes. The Voyager probes, launched in 1977 to take advantage of a rare alignment of the outer planets that occurs only once every 175 years, have become the most traveled objects ever built by human hands. Voyager 2 is the only spacecraft to have visited all 4 outer planets, Jupiter, Saturn, Uranus, and Neptune, completing a grand tour that revealed each world in detail for the first time. At Neptune, Voyager 2 flew within 5,000 kilometers of the cloud tops, discovering 6 new moons, a system of rings, and the Great Dark Spot before continuing outward. The entire mission depended on the precision of the initial launch and a series of gravitational slingshot maneuvers that required years of trajectory calculations, using computers a fraction as powerful as a modern smartphone. Each slingshot, using the gravity and orbital motion of a planet to accelerate the spacecraft, added velocity without consuming propellant, a technique called gravity assist that has since been used in nearly every outer solar system mission. The Cassini mission to Saturn, which operated from 1997 to 2017, is considered one of the most scientifically productive planetary missions ever flown. Over 13 years in orbit around Saturn, it made hundreds of close flybys of Saturn's moons, sent the Huygens probe into Titan's atmosphere, the most distant soft landing ever achieved at the time, discovered the plumes of Enceladus, and determined they contain the ingredients for life, mapped the ring system in extraordinary detail, observed massive storms in Saturn's atmosphere, including a planet-encircling storm in 2010 and 2011, and transformed our understanding of the entire Saturnian system. When Cassini ran low on propellant in 2017, mission controllers deliberately flew it into Saturn's atmosphere, the grand finale, in part to prevent contaminating Enceladus or Titan with Earth microbes. The spacecraft made 22 passes between Saturn and its innermost rings before the final dive, sampling the ring particles and the upper atmosphere directly for the first time. The last signal from Cassini was received on September 15, 2017. It had been traveling for 20 years. It burned up in Saturn's atmosphere, its atoms mixing with the world it had studied so long. The New Horizons mission to Pluto represents another kind of epic. Launched in January 2006, it was the fastest spacecraft ever launched at that time, departing Earth at a speed of about 58,000 kilometers per hour. Even at that speed, it took 9.5 years to reach Pluto. During the approach, the spacecraft was put into hibernation for extended periods to preserve its systems, periodically waking to check its trajectory and send status reports. When it arrived at Pluto in July 2015, it had a single flyby opportunity, one chance, one pass, to collect as much data as possible. The flyby lasted about 9 hours at closest approach. The bandwidth limitations of deep space communication meant that it took over a year to download all the data collected during those hours. Every image, every measurement, every byte was transmitted across more than 5 billion kilometers of space, at a rate roughly comparable to a slow dial-up internet connection. And what it revealed changed our understanding of what small, distant, cold bodies in the outer solar system can be. Active, complex, geologically diverse worlds with nitrogen ice mountains and methane snowfields, and a possible subsurface ocean hidden beneath Pluto's icy shell. The Mars exploration rovers, Spirit and Opportunity, launched in 2003, were designed for a 90-day primary mission. Spirit operated for over 6 years before becoming stuck in soft soil and eventually going silent in 2011. Opportunity operated for nearly 15 years, covering over 45 kilometers of Martian terrain, the longest distance ever driven by a rover on another world, before the global dust storm of 2018 cut off its power. The Curiosity rover, still operating as of 2024, landed in August 2012 and has been driving through Gale Crater, a former lakebed, for over 12 years. It confirmed that Mars once had conditions suitable for microbial life, liquid water, the right chemistry, a relatively benign radiation environment, and that these conditions persisted for perhaps hundreds of millions of years. The Perseverance rover, landed in February 2021, carries the most sophisticated astrobiology payload ever sent to Mars, including an instrument called MOXIE that demonstrated the production of oxygen from the Martian atmosphere, a proof of concept for the in-situ resource utilization that future human missions will require. Perseverance also carried the Ingenuity helicopter, the first powered, controlled flight on another world. Ingenuity was designed to demonstrate that flight on Mars was possible. Its design mission was 5 flights. As of 2024, it had completed over 70. The Martian atmosphere is about 1% the density of Earth's, which means generating lift requires rotor blades spinning much faster than a helicopter on Earth. Ingenuity's blades spin at about 2,500 revolutions per minute, roughly 5 times faster than a terrestrial helicopter. Each flight is autonomous. The communication delay between Earth and Mars makes real-time control impossible, and the helicopter must navigate, avoid obstacles, and land entirely on its own based on pre-uploaded commands. Seeing a helicopter fly on Mars was described by members of the team as the moment they stopped being engineers for a few seconds and became the children they were when they first fell in love with space. The Deep Space Network, NASA's global array of large radio antennas in Goldstone, California, Madrid, Spain, and Canberra, Australia, is the infrastructure that makes all of this possible. These antennas, the largest of which are 70 meters in diameter, track and communicate with spacecraft throughout the solar system and beyond. They receive the faint signals from Voyager 1, 22 billion kilometers away, signals so weak that the power arriving at Earth is roughly 20 femtowatts, 200 quintillionths of a watt. The antenna must know precisely where in the sky to point. The signal must be teased out of the noise of the universe with extraordinary precision, and the commands sent back must account for the fact that they will take over 22 hours to arrive, meaning every instruction sent to Voyager must be written knowing exactly where the spacecraft will be and what it will be doing 22 hours from now. This is routine work for the team at JPL. They do it every day. The development of telescope technology has a history as rich and surprising as the discoveries it enabled. When Galileo first turned a telescope toward the sky in 1609, he saw the moons of Jupiter, 4 points of light that moved around the planet over successive nights, and immediately understood their significance. They were moons orbiting Jupiter, demonstrating that not everything in the solar system revolves around Earth. He saw the phases of Venus, demonstrating that Venus orbits the Sun rather than Earth. He saw mountains on the moon, destroying the idea of a perfect, unchanging celestial sphere. He saw more stars in the Milky Way than were visible to the naked eye, hinting at the depth and population of the galaxy. Within a year of pointing his telescope at the sky, he had demolished the cosmological worldview that had dominated Western thought for nearly 2,000 years. He was placed under house arrest for the rest of his life for defending the heliocentric model. The history of astronomy is full of moments like this. Moments where a new instrument or a new technique reveals something that forces a fundamental revision of our picture of the universe. William Herschel, scanning the sky in 1781, found Uranus, the first new planet discovered since antiquity, and the discovery that demonstrated that the solar system extended beyond Saturn. His sister Caroline, who assisted him and conducted her own systematic sky surveys, discovered several comets and deep sky objects, and became one of the first women to be officially recognized for scientific work, receiving a gold medal from the Royal Astronomical Society. Edwin Hubble, in 1923, resolved individual stars in the Andromeda Nebula, as it was then called, using the new 100-inch Hooker telescope at Mount Wilson Observatory, demonstrating that what had been thought to be a nebula within the Milky Way was actually a separate galaxy, an island universe of hundreds of billions of stars. This single observation multiplied the known size of the universe by an essentially infinite factor. Overnight, everything we had called the universe, the entire Milky Way, was suddenly just one of countless such systems stretching to distances beyond all previous imagination. Vera Rubin, working in the 1960s and 1970s, measured the rotation curves of galaxies and found that the outer edges rotate far too fast to be explained by the visible matter alone. Her work provided the strongest early evidence for dark matter, though she was not awarded the Nobel Prize for it, an omission widely regarded as one of the most glaring oversights in the history of that award. She died in 2016. The Nobel Prize is not awarded posthumously, so she will never receive one. The Vera Rubin Observatory, now named in her honor, will be one of the most powerful astronomical instruments ever built when it begins full operations. Cecilia Payne-Gaposchkin in 1925 showed that stars are made primarily of hydrogen and helium, overturning the prevailing view that they had compositions similar to Earth. Her finding was initially rejected by the leading astronomer of the time, Henry Norris Russell, who told her the result was impossible. He later accepted it and published a similar result, largely without crediting her. She is now recognized as having made one of the most important discoveries in astrophysics, that hydrogen is by far the most abundant element in the Sun and in the universe, which is foundational to our entire understanding of stellar physics and cosmic chemistry. Her doctoral thesis, submitted at Radcliffe College in 1925, was later called the most brilliant PhD thesis ever written in astronomy by Otto Struve, one of the leading astronomers of the mid-20th century. The history of astronomy is inseparable from the history of who was allowed to do astronomy and who was not. Women at the Harvard College Observatory in the late 19th and early 20th centuries, working as computers, doing the detailed numerical work of classifying stellar spectra, made discoveries that changed the field. Henrietta Swan Leavitt discovered the period luminosity relationship for Cepheid variable stars, the very calibration that Hubble used to measure extragalactic distances, that ultimately led to the discovery of the universe's expansion. Annie Jump Cannon classified the spectra of over 350,000 stars, developing the stellar classification system still in use today, the OBAFGKM sequence. These women were paid 25 cents an hour. Their work underlies modern astronomy in ways that are rarely given sufficient weight in popular histories of the field. The Hubble Space Telescope, which launched in 1990 with a famously flawed mirror ground to the wrong specification, a flaw that was corrected in a servicing mission in 1993 by astronauts who installed corrective optics in a feat of precision spacewalking, has been the most scientifically productive astronomical instrument in history. The images it has produced, the pillars of creation, the Hubble Deep Field, the Ultra Deep Field, images of planetary nebulae and galaxy collisions and supernova remnants are part of the cultural fabric of how humanity thinks about the universe. They have appeared on album covers and in museums and in the backgrounds of political rallies. They have made the universe visually real for billions of people who would never otherwise have a reason to think about it. The Hubble constant that bears Edwin Hubble's name, the rate of cosmic expansion, was one of the key measurements the telescope was designed to make, and it made it. And in doing so, it contributed to the discovery that the expansion of the universe is accelerating, which changed cosmology forever. There is something important in all of this that goes beyond the specific facts. Every object we have discussed, every neutron star and quasar and exoplanet and dark matter halo, was discovered by someone, by a specific human being or team of human beings, who built or used an instrument at a particular moment in time and saw something no one had ever seen before and understood, at some level, what they were looking at. Science is not abstract, it is done by people. It is funded by societies that make choices about what to invest in. It is shaped by cultural assumptions about who can participate, what questions are worth asking, what results are worth taking seriously. The history of astronomy shows that when we expand who is allowed to do science, the science improves. When we invest seriously in the instruments and the missions, we discover things that transform our understanding. When we let curiosity lead, when we build a telescope just to see what is out there, without knowing in advance what we will find, the returns are beyond what any prior calculation could have predicted. The next generation of telescopes is extraordinary. The extremely large telescope, being built in Chile, will have a primary mirror 39 meters across, almost 5 times the diameter of the largest existing optical telescopes, and will be capable of directly imaging exoplanets, studying the first stars and galaxies, and measuring the properties of dark matter and dark energy with unprecedented precision. The Square Kilometre Array, a radio telescope being constructed across South Africa and Australia, with a total collecting area of about 1 square kilometer, will be the most sensitive radio telescope ever built, capable of detecting faint radio signals from the earliest galaxies and searching for pulsars throughout the Milky Way. LISA, the Laser Interferometer Space Antenna, is a space-based gravitational wave detector planned by the European Space Agency, consisting of 3 spacecraft in a triangular formation with arm lengths of 2.5 million kilometers, designed to detect gravitational waves at frequencies inaccessible to ground-based detectors, including the mergers of supermassive black holes and the signals from compact binary systems throughout the galaxy. These instruments will answer some of the questions we have. They will also discover things we have not yet thought to wonder about. That is how it has always worked. Every major observatory in history has made discoveries that were not anticipated when it was built. The universe is more inventive than we are. It contains objects and phenomena we have not yet imagined. The next great surprise is out there, waiting for an instrument sensitive enough to catch it. And here, perhaps, is the most important thing to carry forward from everything we have explored today. The universe is 13.8 billion years old. The Earth is 4.5 billion years old. Complex multicellular life has existed on Earth for about 600 million years. Modern anatomically human beings have existed for about 300,000 years. Written records go back about 5,000 years. The scientific method as we currently practice it is roughly 400 years old. Modern astronomy is perhaps 150 years old. The neutrino was detected for the first time in 1956. Gravitational waves were first detected in 2015. The first exoplanet confirmed around a main sequence star was discovered in 1995. We are very, very new at this. We are a species that has been systematically studying the universe for an eye blink of cosmic time, and we have already discovered that the universe is 13.8 billion years old, that it contains 2 trillion galaxies, that its dominant components are dark matter and dark energy that we do not understand, that space-time is curved by mass, and that merging black holes send ripples through it at the speed of light, that planets orbiting other stars have atmospheres and seasons and storms, and that at least 3 moons in our own solar system likely harbor liquid water oceans beneath their icy surfaces. What will we know in another 100 years, in another 1,000? If we survive, if we navigate the challenges of the coming centuries with enough wisdom to remain a technological civilization, what we will know about the universe is beyond prediction. We are at the very beginning. We have just barely started to look. And the universe, patient and indifferent and vast and strange, is waiting